So good morning, everybody. So we have just started the recording of the session. So we will first play a very short introductory video, and then Vario takes over with sharing the first part of this morning.
The following message is best viewed on an oscilloscope. The following message
Okay, so welcome everybody to the second session of the Higgs at ICHEP. Can you hear me?
Yes.
Okay, thanks. So we do have quite a few talks today. We are hoping to see many new results. Today's section is dedicated mainly to a review of the standard model Higgs measurement, including also combination from the two main experiments. A reminder to the speakers to try to stick as much as possible to the allocated time in order to not forcing us to cut down the discussion or the coffee break. And I will notify the speakers when there are like 3 minutes to the end of their talk. So we can now start with the first talk from Matteo. So we can hear you. You can share your slides.
Yes. Okay. Now you should see me.
Yes. Now we can see you.
These are the slides.
And now we can see your slides. They are full screen already. So please start when ready.
Okay. So hello, everyone. My name is Matteo Bonanomi from LLR École Polytechnique. And today I will be presenting Higgs boson measurements in the ZZ and WW final states with the CMS detector. So let's start with a bit of history. As we know, in 2015, LHC started the run-to phase, opening the doors for the so-called precision physics era, in the sense that the main goal of run-to was actually to target precision measurements of the Higgs boson properties. And to do so, Higgs WW and Higgs ZZ are identified as two of the most sensitive decay modes for the Higgs boson. In particular, the Higgs WW decay mode has a large sensitivity coming from its large cross-section and branching ratio values, but on the other side, it has relatively poor mass resolution, especially because of the presence of missing energy in the final state. For what concerns the Higgs to ZZ, we can profit from a large signal to background ratio, an excellent resolution, and a completely resolved final state. These are the key features that allowed us to use this channel since the very beginning, so from the discovery on. However, on the other side, this channel suffers from a limited statistics. These two channels together are actually ideal to study, as we said at the beginning, the intrinsic properties of the Higgs boson. So the mass of the Higgs boson is width, but also the couplings to both fermion and vector bosons. This is something you can do in general already starting from round one. These kind of measurements have been performed, but now we are entering a very exciting phase where we have a really large statistics. In fact, with the full run-to statistics, CMS recorded 137 inverse femtobars. This means that Higgs to WW and ZZ can also be used in order to probe possible EFT couplings. these two couplings with vector bosons can be used also to exploit the full amplitude of XVV, so the coupling with vector bosons. And especially as we see now, we are in a regime where with the current best fit value of the mass, we can access all the different production modes of the Higgs. This means that not only we can study the inclusive properties, but also the pair production mode ones in the so-called simplified template per section framework. That is something we are going to focus in a few slides. So to sum up a bit, ZZ and WW decays of the Higgs boson give access to different properties, as we said. First of all, the intrinsic ones, such as the mass and the width, but then you also have the possibility to study the different production mechanisms, especially with the current run-to statistics. This is something that can be done not only in an inclusive way, so GGH, VBF, and TTH, and so on, but also in a more granular stage. In a more granular description, which is the so-called simplified template cross-section stage 1.1 or above. Then you can also study fermionic and bosonic couplings of the Higgs boson, not only in the standard model assumption, but also assuming some anomalous couplings. And last but not least, you can perform some inclusive and differential cross-section measurements. And these are very exciting measurements because they have been performed with the full run-to statistics, both in the ZZ and WW decay channel. So in my talk, I'm going to focus in the first 4 points that I've described so far. And then I suggest you follow Sava's talk for the anomalous coupling of the Higgs boson description, and Lorenzo talk for the inclusive and differential cross-section measurements. Most of my talk will have also some parallel arguments with Walin talk. All of this talk will be in this session today, in the sense that then you will see same results in the Higgs to gamma-gamma decay channel in Walin talk. So let's start with the measurement of the inclusive properties, starting with the mass of the Higgs. The Higgs to ZZ channel was used with 2016 data in order to measure the mass of the Higgs. As we see here, this was a likelihood scan measurement involving all the 3 different decay channels of the Higgs to ZZ into 4 lepton. So the 4 mu, 2 e2 mu, and 4 electron. The combination led to a final value of 125.26 GeV plus or minus 0.21 GeV. This value is actually already very precise and has been used more recently for the to obtain the best fit value of the mass quoted by the CMS collaboration, which is 125.38 plus or minus 0.14 GeV. And in order to get to this value, we used the Higgs to ZZ into 4 lepton measurement combined with the Furan-1 measurement and the Higgs to gamma-gamma measurement. And already here you see that the final value is mostly driven by this Higgs to ZZ decay channel. On the other side, we can also measure in an inclusive way or in an inclusive sort of picture of the Higgs boson its width. Its width is something somehow delicate, as we know, in the sense that it depends especially on the region, on the kinematical region where you are to probe this measurement. It depends the constraints that you can put. There are 2 regions. The first one is the one that I highlight here in the red box, and this is so-called the on-shell region, where the cross-section is proportional to the inverse of the width of the Higgs. However, in this region, you are really sensitive to both production and decay kinematics, and you can only set upper limits to the width of the Higgs. On the other side, you have the off-shell region, where the cross-section does not directly depend on the width of the Higgs. So normally what you do is to combine these 2 regions, and from the ratio, you can extract a direct limit or measurement on the width. And the yields and the kinematic in this region here are also sensitive to anomalous couplings, and probably you will hear more on this side in Sava's talk. So for what concerns the on-shell region, with the 2016 data set, the Higgs, the Higgs to ZZ for lepton decay channel was used in order to set an upper limit on the width of the Higgs. And as you see here, the upper limit is not really stringent in the sense that you can put a limit at 1 GeV for the mass of the Higgs. Of the Higgs, and this was only with the limited statistics in the sense that you only had 2016 statistics. More recently, a combination of the on-shell with the off-shell region allowed to probe a more extended kinematic range, of course. And this allows you not only to set a more stringent limit, we see here that now we are in the MEV scale, but also to perform an actual measurement, in the sense that now we are not only just putting upper limits, but we are really starting to measure the width of the Higgs, starting also to put lower limits. And in this case, the measurement was a full 2016 plus 17 data set along with a run-1 combination. And in this specific measurement, assuming the standard model-like couplings, we observed a width of the Higgs of 3.2 plus 2.8 minus 2.2 MeV with an expected value of 4.1 along with these errors that you have here. So let's now move in a bit deeper view of the Higgs boson. And so in this so-called study of the production modes, as I said at the beginning, the first very basic thing you can do is to study the production modes in an inclusive way, right? So what you would have here would be the study of the GGH, well, BBF, BH, and TTH production modes. This was the so-called simplified template cross-section stage 0, but as we see in these plots, in these charts, we are now fragmenting even more the kinematic regions of all the production modes. So what are these charts that will be accompanying us throughout all the session, and why are they called simplified template cross-section framework? So the STXS framework is a framework that is aiming to minimize the impact of theory on our measurements without losing any sensitivity. There are different advantages of using this such a framework. First of all, you are performing cross-section measurements without having the theory dependence or the theory uncertainty embedded in it. The second thing is that getting out the theory uncertainties from the measurement, you're actually minimizing any possible dependence on any assumption, on any model assumption. You have kinematical regions directly studied to probe BSM effects, and especially this framework becomes also very handy when you have to compare different results coming from different experiments or analysis, or when you have to run a finite combination. So as I said, in the first stage, you have to categorize event, and you can do it following different strategies. Here I report the one used in ZZ into 4-lepton analysis, where starting from a ZZ candidate, then there is mutually exclusive categorization based on different information, such as the number of jets and B-jets, matrix element-based discriminants. Then you also use the number of additional leptons to categorize in an exclusive way your ZZ candidate in one of these 7 categories. These 7 categories are actually targeting directly the production modes, as we see here. But then, since we are running a full run-2 analysis, you can also profit from a larger statistics and essentially add another categorization on top of this one, which is a categorization done in a finer way in order to match the simplified template cross-section stage 1.1 bits. As we see here, we still have the different production modes, but now all the different production modes can be categorized in a finer binning, with a finer binning, and this is what we see, what we have seen in the previous slide in the so-called simplified template cross-section framework. So when you merge all the categories together in order to study the inclusive production modes, what you can get are, again, cross-section measurements without the getting out the theory prediction, as we see in both plots. On the left, you have the measurement for the simplified template cross-section stage 0, which is actually targeting, as we see in both plots, the production modes. For the X to WW measurement, this was a 2016 dataset analysis, and this was the analysis that allowed us to observe for the first time the X to WW decay channel in CMS. On the other side, you have another appealing measurement, because this is a Higgs for lepton measurement, but with a full run-2 dataset. So this is a legacy result, and in both cases, we see a good agreement with the standard model expectation. And in both cases, you see that you're measuring cross sections, and they allow you essentially to study the different production mechanisms. But of course, this can be pushed forward when dealing with a lot of statistics, especially in the ZZ for lepton case, you're running a full run-2 analysis. So what is done, and this is the plot you've seen a couple of slides ago, is actually a finer splitting of the different production modes. Here we still have the same color code, and you see that in the previous slide, or in the first approach, you want to measure the inclusive GGH, for example, cross-section, but then what you can do is to measure the cross-section in each one of these single beans. And this is what is done in slide 20.
You have 3 minutes.
Okay, thank you. What is presented in slide 20. You see that you can measure cross-sections in all the different beans, again, with the theory not being embedded in the measurement, and you measure ratios to the standard model, and the agreement also here has been found to be consistent with the standard model. But on the other side, you can also remerge all the beans and include again the theory prediction to measure signal strengths. So this really depends on the approach you're taking. But as we see, once you have full data set and you have a sophisticated analysis, you can target different production modes or different kinematical regions and nail down very precise aspects. As we see here, not only you can measure inclusive signal strength and per production mode, but we are really entering a precision phase here, which means already seen in the inclusive and GGH signal strengths, statistical and systematical components are really getting at the same level. And so this is becoming a really challenging and precise measurement. On the same page for the Higgs to gamma-gamma decay channels, you will see more in Pauline talk later. Again, as I said at the beginning, you can also measure, in order to decouple the effects, fermionic and bosonic coupling. So both the analysis WW and ZZ introduced this mu-F and mu-V signal strengths. And in this case, nothing surprisingly, you still observe an agreement with the standard model, and the measurements are not so far one from the other, even if performing two different decay channels. So last but not least, I want to spend a few words on cross-section measurements. You can measure cross-sections in a fiducial phase space, and you can do it both inclusively as a report here for the ZZ on the left, on the right, and WW on the left, or differential. Here for the differential, I show you the differential cross-section measurement in transverse momentum of the Higgs, because it's an interesting measurement in the sense that it's sensitive to possible deviations from the standard model, especially at high PT, at high transverse momentum. But on these, I will not focus more, as you have the dedicated talk from Lorenzo later on today. So this brings me to my conclusions. Today, we presented the most recent X to ZZ and WW results with the CMS. We identify these two channels as being ideal channels for the Higgs boson properties measurement in CMS or LHC in general, especially now that we are entering a phase where the measurements will starting to be dominated by systematics, since we have a lot of statistics coming from run 2. On the WW side, especially in the fully leptonic decay channel, the results have been presented. It's worth to mention that one of these analyses was the first one to observe the X to WW decay in CMS. But then the most appealing measurement is, of course, the differential cross-section measurements, in the sense that this is the first time that in this decay channel, a differential cross-section measurement study has been performed. On the ZZ for lepton side, also very interesting measurements, because beside being used for the mass and the width determination, a huge or an extensive set of results has been performed and produced for the full run 2 statistic. And this includes both signal strengths, cross-sections, but also the so-called simplified template cross-section framework. All the results so far have been found to be consistent with the standard model, but great times are ahead. And so stay tuned for the next steps of this analysis. Thank you very much.
Thanks a lot, Matteo. That was a great start. And also thanks for introducing some of the concepts that we're going to see repeatedly in the next talks. So question time. Anybody wants to go first? Okay, I think that people still need a bit to wake up, so I would like to ask you the first question, which is related to the X2ZZ STXS measurement.
Yes.
Could you say a bit more, like say, which actual discriminant you are fitting in each of the regions?
Yes, so maybe I have a backup slide for this. In the X2ZZ for lepton analysis, the fits are performed, they are two-dimensional fits. One of the dimension is the mass of the 4-lepton, so the invariant mass of the 4-lepton. The other dimension is a kinematic discriminant computed by Mela. And the first discriminant that we used, and this is used both in the fitting and in the categorization, is the kinematic discriminant to discriminate against GGH and QQ to ZZ processes. And so this is the first discriminant to really nail down what is signal and what is background. And then you have dedicated production dependent discriminants, such as the one in the VBF2JET or the VH hadronic tag categories. They are presented here, for example, and here you have the dedicated discriminants. So they are all matrix element discriminants that can be used in order to probe the different, especially the different jet multiplicities, phase space regions that we are targeting. So you have the VBF against the GGH to jet 1, and the same thing for the 1-jet, and then 2 dedicated discriminants for the VH, so WH and ZH production modes.
Okay, so in each of the category that you have shown previously, you fit a 2D discriminant.
Yes, exactly. In each of these categories is created a template, and then this is what is fit along with the information of the mass. But of course, each one of these categories might have different discriminant, especially the VBF-like and the VH-like, they have dedicated discriminants.
Okay, thanks. So Andrea, I don't know which one, but you can speak.
Ciao, Andrea from Atlas.
Hello.
Andrea Gabrielli from Atlas. So very nice talk. Thanks a lot for these results. Just a quick question, slide 20. So you have some bin in STXS where you have 0 observed event also in your RECO categories.
Yes.
And I saw that you provide the results and the covariance matrices so that theorists can reinterpret your results in their model. Just for curiosity, did you check in the case where you have 0 observed events that the coverage that they can extract with your information is still reliable, let's say? Sorry,
I didn't get really the question. You mean when we have 0 events, if we still can somehow trust?
Yeah, if the asymptotic approximation is still valid. Because in line 19, you have some categories, 2 or 3 categories, no, 4, where you have 0 observed events, right?
Yes, that's right. Well, in these categories, you have, we have problem of sensitivity, of course, because we don't have events. But in principle, these fits, as you see, they have like 100, at least 100% of uncertainty. So they are already covered by the lack of statistics that you have in these bins. So they have such a large uncertainty that you're not really worried about the fact that you are fitting at 0 these values. And also when you run these fits, the POIs, so the fitting values are actually bounded, lower bounded at 0. So you don't have the other, let's say, the other side of the error. But of course, if you would fit, for example, between -5 and 5, then maybe you would have even a larger error, and still the point being fitted at 0 with the central value at 0. So if you want, this is just a confidence interval and not really a fit at 0 for the value itself.
Okay, thanks a lot.
Okay, thanks. I think we can, thanks a lot, Matteo, for the talk, and we can move to the next talk, still from CMS, so Ulin.
Yeah, can you hear me?
Yes,
Okay.
Still don't see slides,
Yeah.
or you?
Now you should see me.
Okay, I see you.
Now let me share the slide. Okay,
Perfect.
I assume
Yes,
you can
okay.
see it. Okay.
Yes, start when ready.
Oh, cool. Oops. Okay, I'll start. So today I'm presenting the Higgs boson measurement in final states with photons and CMS. A brief introduction to the Higgs diphoton decay. It has a small branch refraction with clean final state. It has excellent diphoton environment distribution resolution thanks to the CMS detector. And with photon 2 statistics, we are sensitive to all the Higgs major production modes here. It is one of the most important channels for precision measurement of Higgs boson properties. Since round 2, CMS has delivered a series of cross-section measurements with round 2 data, starting from using 2016 data only to probe signal strengths, simplified template cross-section stage 0, coupled modifiers, to recent dedicated paper to QTH production and its CP property. And more details on this subject will be covered by later talks by Sergio and Service. This talk mainly presents a more comprehensive measurement of Higgs boson properties in terms of signal strengths, simplified temperature cross-section stage 1.2 coupling modifiers with the Higgs diphoton decay channel with 4-on-2 dataset. Let me start with the most important object in this analysis, photon. So we correct photon energy with a multivariate regression technique to account for imperfect reconstruction effect, and this also predicts the uncertainty of photon energy. In addition, we use D2E events to drive additional corrections, and this correct drift of energy scale in data over time as a function of LHC field, and also correct energy scale in data and energy resolution in simulation. To do this, we basically align dielectron mass distribution between data and simulation. On the left plot, you see after all these corrections, the dielectron event mass distribution agrees well between data and simulation. On top of this, we use IDBDT to try to separate real photon from fake photon mimicked by jets. And this photon BDT is trained on gamma plus drag events with the following input variables. Two important input variables are shower shape and isolation variables. Their distributions are corrected in simulation so that they agree with data. We use a new method based on a chain contour regression technique with electrons from D2E to correct these input variables. And the goal is to ensure the correlation between corrected variables in simulation are closer to those in data. On the left is a demonstration of the photon ID score for signal-like events. You can see from the blue histogram, and the background-like events were in the red histogram. On the right is the validation of the photon ID BDT using D2E events. Looking at the good data molecular agreements, we're confident about the BDT we're using. So let me now introduce the analysis strategy based on STXS framework. So thanks to the previous talk, I don't have to spend a lot of detail here. So here is only an illustration of the STXS bin definition for GGH at stage 1.2. And we built our analysis strategy based on the goal to targeting as many different stage 1.2 STXS bin as possible. And this allows us to measure all major Higgs production modes with 4-on-2 datasets. And with this setup, we're also sensitive to measure the signal strength modifiers and the coupling modifiers in the Kappa framework, as has been done in previous histogram analysis from CMS. So lastly, let me emphasize that we extract the final measurement meaning cross-section, mu and kappa, by performing a simultaneous fit to gamma distribution in each analysis category. Here is the illustration of the diphoton event mass distribution for 4-on-2 data with all event categories merged together. And here around 125 GeV, we see a nice peak here. As a side note, all the measurements presented in this talk are performed by MH fixed at 125.38 GeV, which is the current best Higgs mass measurement performed by CMS. So let me spend more time on introducing the event categorization strategy. For phase spaces that are sensitive to different Higgs production modes, they are further divided to explore different STXS bins. Due to current statistics, we're not able to measure every single bin. So in these cases, we need to merge them due to the lack of statistics. And in each of the STXS bin being considered like all this little blue box, we further divide events into analysis categories based on dedicated BDTs or DNNs, with the goal to reject backgrounds and maximize expected sensitivity. So in total, we have 81 categories considered in this analysis. And here is a demonstration of the analysis category composition in terms of the STX stage 1.2 bins being considered. By looking at the events populated along the diagonal line, we can see that our analysis categories are pure enough in terms of the STXS bin they're targeting. Now let me use group confusion events as example to illustrate how we do event categorization. So first, in this case, we use a multi-class BDT with 9 classes to predict the probability that an event belongs to a given GGH STXS bin, as shown on the left plot. It's a validation of the multi-class BDT used in GGH. From this validation, we can see we use data molecular agreements for all the 9 STXS bins being considered. It has a 5% improvement in terms of accuracy of bin assignment. In each of the STXS bins being considered, we further divide events into subcategories based on different S over B. We use the diphoton BDT. And the goal is to reject backgrounds from standard model diphoton production. And this diphoton BDT is trained using photon kinematics as input variables. Here is a performance plot for the diphoton BDT with the blue histogram showing gluon fusion events and the red showing other backgrounds. As I said, we also consider all other Higgs production modes, BBF, VH, PTH, and TH. Here is only a selective plot showing the multivariate discriminants used in this analysis. In each of the cases, we can see we have good control of the background composition and the decent data Monte Carlo agreement, which is the basic for our analysis strategy. Here, we have one potential ambiguity, which is one event can possibly pass event selection for more than one analysis categories. To tackle this, we define priority strategy, meaning analysis category with lower expected signal yield will have higher priority, so that when the events have the possibility to enter more than one analysis category, we assign it to the category with highest priority. Now I'd like to introduce a few of the highlights from this new analysis. First, we have new comprehensive categorization for VH events. This is new in terms of previous histogram gamma analysis from CMS. And now we also have a dedicated categorization for THQ events, targeting THQ leptonic events. And in events, in certain categories, for example, VBF, VH mat, PTH hydronic, we use data-driven estimation for certain key backgrounds to improve the performance of MVA training, thanks to the good understanding of input variables and increase of training statistics. And unfortunately or fortunately, the analysis of each production mode can be easily expanded to a full talk, and you will find more details in backup, and I'm happy to discuss more details in discussion. And here is the example of the THQ event candidates with Higgs to diphoton, and there's a muon pattern and muon detector. So now here's the M gamma gamma distribution. On the left is the signal model we considered with all event categories merged together. Here we have an effective resolution of 1.9 GeV. Just a side note, our signal model are derived using simulation where background model are derived using data. On the right, a full M gamma gamma distribution for all Higgs major production modes, gluon fusion, BBF, VH, and top associated. In each cases, you can see a nice peak around 125 GeV. This brings me to the first measurement I present today, which is the Higgs signal strength modifiers, defined as the ratio of observed cross-section times rate refraction to the standard model prediction. Here we have an inclusive measurement of mu with 1 around 10% uncertainty. You also can see here the decomposition of theory, systematic, and statistical uncertainty. We also have measured mu per production mode, decomposed into mu VH, mu VBF, mu top, and mu GGH. Also for mu GGH, we now start to see the systematic uncertainty starts to become dominated. Next, I introduced the measurement of the ST-axis simplified template cross-section. We have two merging schemes. Let me first discuss the minimum merging scheme, which means we have 24 parameters of interest or 24 cross-section measured. In this case, we merged as few ST-axis spin as possible, and the correlation between bins are smaller than 0.75. Each of the regions circled by red box are the cross-section we consider for GGH, and their measured value can be found on these plots above the red line. As a note, these four bins are corresponding to GGH events that are VBF-like, so they are considered together in the QQH scheme with VBF events that are introduced in the next slide. So here is the VBF case, VBF plus VH hydronic decay case. So this bin corresponding to VH, where the vector boson decays hydronically, and these 5 bins corresponding to VBF events. So their measured cross-section can be found on these few values. Now moving on to the other production mode. For VH, we first divide them into WH and ZH. Then in WH, we make a final split at the transverse of momentum of the vector boson at 75 GeV. But here we actually use the PT of the diphoton as a proxy of the PT of the vector boson. That's how we split VH. And for TH, we have 4 splits based on the PT of the diphoton system. And we also have the measurement for TH. Here we have the first measurement with additional 1.2 splitting for TTH and gluon fusion PSMD. And the next slide, I'll quickly describe the maximum merging scheme, where we have 17 parameters of interest measured. Here, the STX schemes are merged until expected uncertainty is smaller than 150%. Sorry, 150% of the standard model prediction. In this case, we also produced the measurement on the TH production, where we have excluded the TH production cross-section at 12 times the model prediction. We also have to measure TH production cross-section times branching fraction to be 0.8 femtobarn with about 100% uncertainty. For the last measurement I'm presenting is the coupling modifiers. Its definition.
You have 3 minutes left.
Its definition has been described in previous talk, so I'll skip it. Now we have two models considered for coupling modifier measurement. One is the resolved model, where the scaling factor of GGH and Higgs gamma gamma are resolved into their standard model components in terms of other couple parameters. Here we present a 2D scan of couple V, which is the coupling modifier between vector boson and Higgs, and kappa F, which is the coupling modifier between Higgs and fermions. In this case, we exclude the region with negative kappa F with about 1 sigma significance. We also have the unresolved couple model measured here, where the GGH and Higgs gamma gamma loop have their own effective scaling factors. Summary. Here I present the Higgs gamma gamma analysis based on Furon-2 dataset collected by CMS detector during Furon-2 during full L02. And we have impulsive signal strength measurement, per production mode signal strength, and coupling modifier measurement. They are all consistent with standard model prediction. We also perform cross-section measurement under the simplified temporal crossing framework at stage 1.2. Here we have considered two beam merging scenarios, each with 17 and 24 cross-sections being measured. We also set exclusion limit on TH production, which is the first time has been done in CMS Higgs gamma gamma analysis. Here we also have the first measurement of TH cross-section in 4 beams of Higgs boson transverse momentum. And there are many more Higgs property measurements with the Higgs diphoton decay trend ongoing. Please stay tuned. Finally, let me end my talk with this summary plot. Since its discovery, the Higgs gamma gamma analysis in CMS has gone a long way, and the investigation will continue until starting from 2020. Thank you.
Thanks a lot for showing this brand new result. We go directly to questions, since there is already one. Chen?
Yes. So, yeah, thank you for the...
I cannot hear the question.
Chen, we cannot hear you anymore. Do you maybe want to type your question? In the meantime, we ask other people if they have a question. Marco?
Yeah, thanks for the nice talk. I was wondering if you can say something more about the correlation. You mentioned this correlation smaller than 75%, seems a bit large. Do you have any correlation table on your STX results?
Yeah, let me go to the backup slide. Okay, so here is the correlation matrix in the minimum merging scheme that I was describing more carefully. So the large correlation is mainly come from the correlation between TH and TTH, where we have the highest PT of the Higgs. That's where the highest correlation coming from. It's understandable because in the TH events we tend to have higher higher PT of the Higgs due to the boosted topology, and that's coincide a little bit with the phase space we're considering for this TKH beam. For the others, the correlation is not that high.
Thank you.
Okay. More question? Maybe I have one, if I may. So could you say a bit more about how much is the contamination of the various production mode in each categories? Like if you go to slide 21, when you're plotting here the signal and the weighting, it's all based on the overall signal or of the main signal targeted by each of these plots?
It's by It's by each of the main production mode we defined by a set of pre-selection.
Okay, but so for instance, like in these plots, when you go to the GGH category, or better, let's say the TTH category, when you do S over B weighting, the S is just the TTH signal, or it's the sum of all the production
okay.
modes?
The S here is the signal considered only in TTH selection.
Okay. Okay, more questions? Yes, Chan, we can hear you.
Okay. Yeah, sorry, I dropped out. So I just wonder what's the source of the larger correlation between TH and the TTH measurements?
Okay. I don't know if you hear, but let me repeat briefly. The largest correlation is the TH and the TTH, where the Higgs have the highest PT. Other than that, the correlation is not that high.
There are contaminations in the categories, so I mean, you have TTH events in TH categories, so they are correlated because of this.
I see, thanks.
Okay, last chance for questions. This is a brand new result. Okay, it doesn't seem so. If not, thanks a lot again, Walin, for the nice slides, and we move to the first talk from Atlas of the session.
Hello.
Hello, Antoine. We can see you, and we can see your slide as well.
Okay, perfect.
So you can start when ready.
Okay, so let's start. So hello, everybody. Good morning, good afternoon, or anything for the people watching this in replay. So I'm Antoine Laudrin, working at the Mainz University in Germany, and I will present you some Atlas results on the Higgs differential cross-section in the 4-lepton and gamma-gamma decay channel, and Higgs mass measurement in the 4-lepton decay channel. So let's start straight with the differential cross-section in Higgs to 4-lepton and Higgs to gamma-gamma. So this comes from two results. The Higgs to 4-lepton one is from a paper which is now accepted in EPJC and is the final run-2 result for this channel. The Higgs to gamma-gamma results come from a conf note that was released last year. So the results are still preliminary and the paper is being finalized now. So welcome everybody to the Higgs precision measurement era. So what do we do as measurements? So this was mentioned already by Matteo Bonanomi in the first talk. We can do fiducial cross-sections, which are measurements which are largely model independent and mainly target the decay side of the measurements. So basically you define a fiducial phase space around your detector or acceptance or analysis acceptance. And this provides you the measurement. But then if you want to combine with other channels, you need to extrapolate to the total phase space, which is common to all analyses. On the side of the simplified template cross-sections, STXS, this one are defined to reduce the theory systematic, but are slightly more model dependent. They mainly target the production side, meaning they are common to all decay channels and therefore easier to combine. They also define some BSM-specific regions, which are easy to interpret as BSM physics. And then some higher level interpretation from that. So we are looking for BSM physics through very precise deviation of the standard model. And we can interpret the result in terms of pseudo-observables, in terms of effective field theory, or couplings modifiers in the kappa framework, or any preferred interpretation framework you could find. So in this talk, I'm going to focus on fiducial cross-sections. For the STXS talk, I will refer you to Lisa Misovic's talk, which will happen in half an hour. And in terms of interpretation, I will give you some examples in terms of pseudo-observable, effective field theory, and kappa framework as well. So let's have a quick glance at how the Higgs to 4-lepton and Higgs to gamma-gamma analysis are performed. So both of them have a fully reconstructed final state, which means they have a very good precision in their measurements. In the 4-lepton case, so you see the mass distribution, the Higgs mass distribution in both channels. So in the 4-lepton case, the final state is 4 leptons, so electrons or muons, to keep this precision high. And they have a rather low PT, and they are isolated. The main background, which is in red here, is the continuum QQ to ZZ process. Its shape is taken from the Monte Carlo, but its normalization is taken from the sideband in the data. The branching ratio is quite low, but the signal to noise ratio is about 2, meaning that we can easily see this X peak here in blue on the plot. For the X to gamma gamma channel, the final state is two isolated photons. The main background is also a continuum, so gamma gamma continuum, which is estimated from the data sideband as well. The branching ratio is a bit higher, but the signal to noise ratio is below 1 to 10, meaning you need this background substrate shape to really see the signal. So how do we do differential cross-section measurements? So first, we start with an input distribution, which is, for example, here, the 4-lepton PT, and it's just a number of count in each bin of the measurement. Then you want to unfold this distribution with regard to the detector effect. So you take a reference shape, the 4-lepton mass or gamma-gamma mass here, and applying a matrix or bin by bin unfolding, you can remove this or cancel these detector effects. And then we can go to fiducial cross-sections, which are really cross-section in the y-axis in each of the measurement bin. And then you can compare this measurement with the Monte Carlo predictions you can produce. And from this measurement, you can provide then higher level interpretation in terms of the framework I described above. So going to the core of the analysis, what do we unfold? Which observable do we unfold? So in the 4-lepton case, we have 20 observables. In the gamma-gamma case, it's at the moment 6 observables, but this is still preliminary. And you can unfold observables in the X system, so X PT or rapidity. In the 4-lepton case, even the sub-decay related variable. Some jet variables, the number of jet, the PT, dijet invariant mass or angular separation, or X plus 1 or 2 jet system. In the 4-lepton case, we also have double differential cross-section, so combinations of the above variables. So let's have a look at some example of differential cross-section. So on the left, you have the X to 4-lepton shape for the leading jet PT, and on the right, the X rapidity in the X to gamma gamma channel. So how to read these plots? You have, in both cases, the data measurement in black, and all the other points are different Monte Carlo results for each of these bins. And on the bottom inserts, you have for X to 4-lepton, the theory normalized by the data for each prediction. And on the right, for X to gamma gamma, it's the data divided by the best Monte Carlo prediction. In both cases, a good compatibility with the standard model is found, as all the measurement points are in agreement with the Monte Carlo generation. Another example is the number of jet, which this one is particularly interesting because it's sensitive to the production mode composition, meaning the relative fraction of GGF, VH, VBF, and TTH. And so 4-lepton on the left and gamma gamma on the right as well. Again, here, all the measurement points are in agreement with the Monte Carlo prediction. So we have a very good standard model compatibility for this measurement here. We can also, so moving to higher level interpretation, we can also provide some constraint on the X to charm Yukawa coupling, or kappa C in the kappa framework. So for that, we use the XPT distribution. So on the left, 4-lepton, on the right, gamma gamma. And for this distribution, at low PT, it's sensitive to the charm or bottom Yukawa coupling, and at high PT, it's sensitive to possible new EV states that could enter the GGF loop. And the distribution are in agreement with the standard model in each cases. And from that, we can put some confidence level interval, some constraint with a 95% confidence interval on kappa C. So in the case of 4-lepton, -7.5 to 9.3, and X to gamma gamma between -19 to 24. The result here is a bit lower than the 4-lepton case because it's only using shape information and not rate information. An example of pseudo-observable interpretation in case of the X to 4-lepton differential cross-section analysis. So for this one, we start from a double differential cross-section, M12 versus M34. So M12 is the mass of the on-shell Z, and M34 the off-shell Z mass. And this, the later, the M34, is sensitive to possible light states that could enter the decay. And from that, we probe pseudo-observable, which are contact terms entering the diagrams, contact terms between the Higgs boson, the Z bosons, and the left and right-handed leptons. So you see the result on the right plot here, epsilon L, so for left-handed lepton versus epsilon R, the right-handed leptons. And again, the distribution is in agreement with the standard model, so the interpretation as well. There is a good compatibility with the standard model within 1 sigma. And last result for the differential cross-section in the Higgs to gamma-gamma case in terms of EFT. So EFTs are a systematic expansion of the standard model Lagrangian. We are restricting ourselves to the dimension 6 terms. And these terms can be expressed in different bases. So here the interpretation is given in terms of Sillage or Smeft basis. And as you see on the bottom left plot, if you turn on some coupling of some EFT coupling, this will change the distribution of PT gamma gamma, NJet, or any distribution. And from that, you can compare to the standard model reference shape and put some constraint on the EFT coefficients as shown on the right plot. So here, same conclusion. There is no significant deviation from the standard model, as everything is compatible with the shape are compatible with the standard model one. And all the constraints are summarized on the right. So let me move to the Higgs to 4 lepton mass measurement. So this is the first Higgs mass measurement using the full run-2 dataset. And this was released in April, I think. So the result is still preliminary, but the paper is being finalized as well. So let me give you a few key elements of the Higgs to 4 lepton mass analysis. So we are looking at the signal region between 115 and 130 GeV, in which we observed more than 300 events with a signal-to-noise ratio of 2/1. And then the name of the game is how can we improve the resolution on the 4 lepton invariant mass? So the first point is to recover the final state radiation, which affects 4% of events, and doing that, improve the resolution by 1%. Then one large improvement we can find is using a Z mass constraint. So the leading Z should be more or less on shell. And given this, we can constrain the lepton kinematics from this Z decay. And this brings a 17% improvement on the 4 lepton resolution. Then, despite having a large signal-to-noise ratio, we still would like to have more pure categories of analysis. So for that, we use a BDT, which is trained to discriminate the Higgs signal versus the ZZ continuum background. And we define 4 BDT bins, and we do the simultaneous analysis in all the bins. This brings a 2% improvement on the mass resolution. So in total, we have 16 analysis categories, 4 BDT bins times the 4 final state, 4 mu to E to mu, 2 mu to E, and 4 mu. Last elements of the analysis. So the signal modeling, it was using a combination of Gaussians, and this has been changed to a double-sided crystal ball, which is more physical. And we also use a per event resolution. So what does that mean? So in short, moving from the lepton resolution to the 4 lepton mass resolution is not that straightforward. So we use a neural network to predict the 4 lepton invariant mass resolution from the lepton kinematics and the uncertainties on these kinematics. And using this, we gain a 2% improvement on the 4 lepton mass resolution. So let's move on the actual result. So these measurements give Higgs mass of 124.92 plus or minus 21 GeV, which is still largely statistically dominated. As you see on the right on this plot here, the comparison between the channel is good, and there is a good compatibility. The leading systematics is the muon momentum scale at the order of 80 MeV.
You have 2 minutes.
Okay, it will be fine. This can be compared to the previous Atlas result using a combination of Higgs to gamma gamma and Higgs to 4 lepton with run 1 and run 2 data, which had an uncertainty of 0.24 GeV. So we have a 15% improvement with Higgs to 4 lepton alone in this measurement. And this could also be compared to the previous CMS result using only Higgs to 4 lepton and only 2016 data, which has the same uncertainty. the takeaway point here is that all results are compatible within their uncertainty at about 1 sigma. So this brings me to my conclusion. So first, on the differential cross-section, I presented the X2 4-lepton final run 2 result and the X2 gamma-gamma result using the full run 2 dataset. It's being finalized at the moment. So we are now at a 10% precision level in the inclusive fiducial cross-section. And in the case of the 4-lepton analysis, it improved the last result by 40%, and it's still largely statistically dominated. In the X2 gamma-gamma case, it's the best inclusive fiducial cross-section measurement up to now in the gamma-gamma channel. This inclusive cross-section measurement is now systematically dominated. All the other differential cross-section are still statistically dominated by construction. The two analyses provide some constraint on the X2 Charm-Yukawa coupling at the 95% level, and some higher level interpretation was provided with pseudo-observable or EFT. In both cases, no significant deviation from the standard model is found, and there is a good compatibility with the theory. And then the Higgs mass measurement in the 4-lepton channel. So this is the first Higgs mass measurement using the full RN2 dataset. It is of 124.92 GeV plus or minus 0.21. It's 15% better than the previous Atlas measurement and at the same level of resolution than the previous CMS H2 4-lepton result, despite a different dataset. And the takeaway point is that all the measurements are compatible within their uncertainties. So thank you very much for your attention, and please stay tuned for other talks on Higgs physics in this session.
Thanks a lot, Antoine, for the nice talk. And question time. So who wants to go first?
I can ask a question on the mass.
Yep.
So your statistical precision on the mass is the same as you say, as the one from CMS in the 4-lepton channel, but using only 2016 dataset. Is it solely due to the 4-muon mass resolution?
Yeah.
Or are there other differences?
I think it's mainly coming from the 4-muon case, which is dominating in both analyses. And the muon resolution measurement for CMS is much better than in Atlas.
Thank you.
Okay, so last chance for a question. Marco?
So maybe a quick one on the EFT interpretation. You show results using different bases. Do you have any clue or whether there is any plan or unifying basis for future interpretation?
Sorry, I didn't get that.
I was wondering, you showed some results using SMET and some other using SILCH. I'm wondering whether you know if there's any plan to unify bases in the future and possibly combine.
For this specific analysis, I don't know, but I think the target is to use SMET as a global EFT basis for Atlas. So I think the analysis first started with CLH, which was their historical basis, and they are now turning to SMET. So
excellent. Merci.
Okay, so we can thank Antoine again and move to the complementary talk from CMS. So Lorenzo.
Hi, I guess you can hear me.
We can hear you, we can see you.
Great, let me share. Okay, can you see the slides?
Yes, please start when ready.
Okay, great. So my name is Lorenzo Vigliani from the INFN of Florence, Italy, and today I'm going to discuss about recent CMS measurements about Higgs boson fiducial and differential cross sections. So given that we are now analyzing the full run 2 LHC data in CMS, with this data we are definitely entering the era of precision physics in the Higgs boson sector. Indeed, most of the inclusive Higgs boson measurements that have been performed are starting to be limited by systematic uncertainties in several channels. As you can see, for example, in the table here, where you can see the inclusive measurements split by production process and decay channel. So the question then is, how can we go ahead and further improve these measurements? So one of the possible answers is to go differential. So measuring fiducial differential cross sections is very important, first of all, to perform a further test of the standard model predictions, but also to probe particular phase spaces that can be more sensitive to BSM effects. So there are two keywords here. The first one is differential, which means measuring the cross sections in bins of some observables that are of interest for some reason, for example, the Higgs boson PT or the number of jets or many others. And the second word is, the second keyword is fiducial. Fiducial means that, as we have seen also in the previous talk, that we extrapolate the measurement to a phase space, which is not the full phase space, but it's a restricted portion of phase space, chosen such that it matches as close as possible the experimental selections. And this is very important because it allows reducing the model dependence that we would otherwise introduce extrapolating to the full phase space, and also means that we can have measurements that have a long lifetime and that can be compared also in the future with possible new theoretical predictions that will come. The main drawbacks of this approach is that usually these measurements are limited to at most 2 variables measured at the same time. And it's also hard, let's say, to combine different channels without extrapolating to the full phase space, because the fiducial phase space is something that is very specific for a given decay channel. And also the definition of the fiducial phase space has to be simple, so it's not trivial to include complex variables that are often used by the analysis, for example, any machine learning approach. So something which is complementary to the differential measurements is the simplified template cross-section framework. So since we have heard already about that in other talks, I'm not going to say anything about the description of this, and you will find the results about this in many other talks during this parallel session. So let me go directly to what I will focus on in this talk instead, which is, as I said, fiducial and differential cross-section measurements from CMS. So in this table, you can see the channel that I'm going to briefly discuss in this talk and the dataset that have been used by each channel. You can find also the reference to the paper or public document just to ease finding more details about each channel. So let me start then from X to WW, which is the most recent measurements from CMS based on the full run 2 data. So this is an important channel because of its large branching ratio and also good signal sensitivity, despite, of course, the large backgrounds. In this analysis, we consider only the full electronic final state, so with 1 electron and 1 muon in the final state. And of course, in this case, we have the neutrinos that prevent the full reconstruction of the Higgs boson mass. So alternatives have to be found to extract the signal in this case. The main backgrounds are WW top quark and non-prompt lepton production, and the contribution of each background depends on the phase space that we are looking into. So in this analysis, we measure as observables the Higgs boson transverse momentum and the number of associated jets, and the signal extraction is performed using a 2-dimensional template fit of the dilepton invariance mass and the transverse mass. So basically, we do this 2-dimensional template fit in each bin of the observable that we want to measure, and we also apply a further splitting in each category in order to enhance the signal sensitivity. Of course, if we want to report a particle level measurement in the fiducial phase space, we have to do the unfolding. And in this analysis, the unfolding is embedded in the electric function. So basically, the unfolded results are directly extracted from the fit. And for the PT Higgs measurement, we also add the regularization penalty term in the electric function. And I'm going to tell you a bit more details about that in the next slides. So going to the measurements. So here you can see the PT Higgs measurement on the left and the number of jets on the right. So a few things to notice here. First of all, if you look at the bin widths for the PT Higgs measurements, so you can see that especially in the low part of the spectrum, the bin widths are in this channel mainly dictated by the PT miss resolution that we have, which is poor in this case because of the neutrinos. But we can measure the cross sections in each beam with quite a good uncertainty, which is around 15% or 20% on average, especially in the low part of the spectra for NJET and PT Higgs. And for both measurements, we see quite a good agreement with the theoretical predictions in all beams. There is only a small discrepancy for the highest NJET multiplicity beam, but it's just 1.4 standard deviation, so nothing especially significant. In addition to the differential measurements, we also perform inclusive measurements for the cross-section in the fiducial phase space. And in this channel, the fiducial cross-section has been measured to be 86.5 femtobarns in good agreement with the standard model expectation. If you look at the breakdown of the uncertainties in the red box here, you can see that already the experimental, let's say the systematic uncertainties are already dominating this kind of measurement. Okay, in addition to the cross sections in each beam, it's also important to report the correlation matrices for the two measurements that you can see here in this slide. In particular, if you look at the left plot, which is the correlation matrix for the PT Higgs measurement, this matrix is split in two parts, the regularized, let's say the correlation from the regularized fit and from the unregularized fit. And it's interesting to see from this matrix that what the regularization is doing, which is what we expect from it, basically tends to smooth out the unphysical anti-correlations among adjacent beams, and also minimize the global correlation coefficient, which is what I mean, it is tuned to do. Of course, for the NJET, which is a discrete variable, we didn't apply any regularization, so the matrix is only one-sided in this plot. Okay, so let me already move to X2ZZ. Also, these results are based on the full run-2 data. So you have already heard the details about this final state, which is a very clean final state despite the low signal lead, but also the background is very low. So in this analysis, the signal extraction is performed fitting the 4-lepton invariant mass, since here we can reconstruct the full Higgs mass, in the different decay channels that are considered, which are 4 electrons for muons and 2 electrons and 2 muons. The strategy of the signal extraction is a bit simplified. In particular, there is no rank categorization and no kinematic discriminant in this case with respect to the, let's say, non-differential analysis. And also in this case, the unfolding is embedded in the likelihood fit, but no regularization is applied in the distributions measured in this channel. So here you can find some of the results related to the Higgs boson distributions, the PT of the Higgs on the left and the rapidity of the Higgs on the right. Also in this case, you can see that we can measure this distribution with quite a good precision, which is around 20 or 30% for all beams of these distributions. And we also find a good agreement with the measurement with the theoretical predictions of Poheg and the LOPS. If you look at the rapidity of the Higgs, you can see maybe a very slight different shape with respect to the theoretical prediction. Of course, this is not significant, but it's something interesting that we can look at it also when we will add more data. Other distributions measured in this channel are related to the number of jets. So number of jets in the left and the PT of the leading jet on the right. Also in this case, you can see that especially in the low part of the spectra, the precision of the measurement is around 20 or 30%. So it's quite good. And in addition to that, we also performed the inclusive fiducial cross-section as for X2WW, which is in very good agreement with the theoretical prediction. And also in this case, you can see that the statistical component and the systematic one are at the same level. So of course, we can improve the measurement with more data, but also we will have to find a way to reduce the systematic for these kind of inclusive measurements. Okay. Let's go now to the X2 gamma gamma analysis. These results are based on 2016 data. So as you have seen already, I mean, X2 gamma gamma is a very clean final state, and it's a very powerful channel for precision measurements because you can reconstruct the diphoton invariant mass with high precision. And in this channel, you can also measure a large variety of observables. So the main backgrounds are gamma gamma, gamma plus jets and dijets. And here the signal extraction is performed categorizing the photon pairs according to their relative mass resolution. And in this way, we define different categories. And in each one of these categories, we fit the diphoton invariant mass spectrum. Of course, this fit is done in also in each bin of the observable that we are going to measure. And in this case as well, as in all CMS analysis, the unfolding is embedded in the likelihood function, and also in this case, no regularization term is included in the likelihood itself. Okay, as I was saying, in this channel, we measure really a lot of observables. This is just a few highlights, and you can find more in the backup slides or in the paper itself if you're interested. So the variable that we measure with the best precision is PT of the diphoton system with an average uncertainty of 40%, which is the plot on the left. I remind you that this is based on 2016. So in this case, we really expect to improve the results when we will analyze the full run-through data. And you can also see here the number of jets in the middle and the rapidity of the diphoton system in the right. In all cases, we find a very good agreement with its theoretical predictions. And something which is interesting to say here is that in this channel, we have also measured double differential distributions, in particular the PT of the diphoton system as a function of the number of jets. And in this case, we have performed the measurement, the cross-section measurement in 9 bins. And this is very interesting because it allows to measure to take into account the correlations between these two observables. And here, just as an example, you can see the PT of the diphoton system for 0 jets on the left, and the PT of the diphoton system for 1 jet events on the right. The other plot is also in the backup slides if you want to see. In this case, the inclusive fiducial cross-section is in agreement within the uncertainties with the expectation. And of course, as I was saying, in this case, the statistical component is larger with respect to the systematic one because this is only 2016 data. Okay, last topic that I want to cover in this talk is a combination of X2 gamma gamma, X2 ZZ, and X2 BB from CMS based on the 2016 data. So in this case, as I was saying, we combine the results from these channels, X2 gamma gamma, X2 ZZ in particular. And in this case, of course, in order to combine them, we extrapolated to the full phase space the results. And we have also included X2 BB bar, especially because this helps constraining the tail of the PT Higgs distribution. So one of the measurements that we perform in this combination is the PT of the Higgs, as I was saying, as you can see in the plot on the left here, which is, it allows to measure this distribution with a nice level of precision. And what I want to point out here is that using these kind of measurements, we can also put constraints, for example, on the Higgs boson couplings to fermions, because it is known that any deviation of the couplings to fermions with respect to the standard model prediction can distort the shape of the PT Higgs. So we can use these measurements to constrain the couplings. So here, just as an example, you can see some of these constraints on kappa B, kappa C, and kappa top. Here, of course, there are some assumptions in these plots, but as you can see, we can put nice constraints on these measurements. And finally, what we have done is to basically use the results that I've shown in the previous slide to, let's say, project at high luminosity. So basically, the idea here is to see what we can measure when we will have 3,000 inverse femtomass of data at the high luminosity LHC. So basically assuming that the CMS detector will perform in a similar way in the high luminosity LHC condition with respect to the run-2 results that we have got, we can extract this kind of measurement that you can see on the left plot, which is very nice because you can see that we can measure the cross-section in each bin with a precision which is below basically 10% in almost all bins. And of course, as before, we can use this distribution to constrain the couplings. In this case, I'm showing just the constraint on C and B quarks. And also in this case, there are some assumptions, in particular, for example, of how the uncertainty, the systematic uncertainties are scaling in the high luminosity LHC conditions with respect to what we are measuring now. But you can see that we will be able to put very nice constraints on these couplings from differential measurements. Okay, so this brings me already to my conclusions. So fiducial differential cross-section measurements are really important to explore even further the Higgs boson physics and also to search for BSM effects. And CMS provided a rich set of fiducial differential results based on LS2 data, but much more are yet to come. So stay tuned for that, for the new results. And it's also nice to see that projections for high luminosity LHC, I mean, it's when we will have access to a high luminosity LHC data, we will be able to improve even further the measurements in the Higgs boson sector. Okay, thanks for your attention.
Thanks a lot, Lorenzo. Very nice result. Questions? So
can I?
Oh yes, Thomas,
yeah.
please.
Yeah. So I noticed in your slide 19, so in the second bin of PTH, there is excess of all these 3 channels above the expected cross section. So how significant is that? Or
yeah, I mean, if you look also at the combination, which is the black point, you can see that the uncertainty band is not so far with respect to the one, let's say. So it's not really significant. I don't know how much standard deviation is that, but it's nothing especially significant. And I remind that this is based on 2016 data for all the channels. So
I
it's
see.
not using the
so
updated X2ZZ result.
Yeah, and the BB bar is not present in this bin, right?
No, BB bar is only in the IPT Higgs bin.
Okay, thanks.
So it's the the green points that you can see in this plot.
Okay, next one, Gaetano.
Hi, this is Gaetano Barone from Atlas. I had just a question regarding the regularization for PT Higgs in the Higgs WW. How much do you gain statistical uncertainty by applying the equivalent constraint, and how much bias do you actually add? Sorry, how much bias do you actually add? Do you have an idea?
So I think I have a table in the backup slides. Let me see. Yes. Okay. So in this table, in the top table, you can see the PT Higgs measurements, the cross section and the signal strengths, and the breakdown of the uncertainty. And if you look at the one, I mean, the column where you can see bias, this is the bias that we have estimated that is coming from the regularization term. So for estimating this bias, we basically have performed some studies with toy datasets. And basically this comes from the average difference that we see from toys and from the, let's say, best fit that we measure. And if you compare these with the statistical component of the uncertainty, you can see that it's not, I mean, it doesn't have a large impact. Of course, we expect the regularization to introduce some bias, as we see here. But we have tuned the regularization strength parameter in order to have as small bias as possible.
Okay, thanks. I also see that it's not that one gains significantly more with the constraint in statistical uncertainty.
Yeah. Yeah, I mean, also these measurements are starting in several bins to be limited by the systematic component, as you can see in this table. So, I mean, it's not, statistics is of course important also for these differential measurements, but it's not the dominant factor, I would say. Well, in some bins it is, but okay, of course.
Okay, time for a very last quick question, if any. Doesn't seem so, so thanks Lorenzo again.
Thank you.
And we go to the next talk, which is from Lisa. Hello, Lisa. We can see you.
Can you see my slides fine?
Yes, we can see the slides, so please start already.
Okay, I'll present measurements of Higgs boson production mode cross sections in Higgs decays to bosons. We have 2 new results with the full run-2 data sets, Higgs to gamma gamma and Higgs to WW in the VBF production mode. And I also briefly discuss the Higgs to ZZ to 4 leptons results, for which we've released a paper a couple of months ago. So as for production modes, the GGF is the dominant one, then the VBF and VH are about an order of magnitude smaller, then almost an order of magnitude smaller is the TTH another order of magnitude smaller is the TH that is typically just merged with the TH, but with the full run 2 dataset, we actually have sufficient sensitivity to make interesting conclusions about it. And then there's the BBH that is about the same size of the TTH, but is experimentally very challenging to measure, and it's typically just merged with the GGF. As for decay branching ratios of the ones we'll consider, the WW is the largest. The gamma has the branching ratio of about 0.2%, and the ZZ to 4 leptons has then an even smaller branching ratio of 0.1%. And we measure these production cross sections in the simplified template cross sections framework, where we take the fiducial, approximately fiducial phase space with Higgs, requiring Higgs rapidity to be smaller than 2.5. And then within this phase space, we target both the production modes as well as specific phase space regions of these production modes. And the kinematic variables we use for this finite granularity are, for example, the transverse momentum of the Higgs, the number of extra jets in the process, and especially for the processes sensitive to VPF, the invariant mass of the 2 jets. So with these STXS regions, what we do then is we design reconstructed categories to target them. And then we can extract the cross sections in each of these regions from the category yields. In terms of run-to sensitivity, in the Higgs to WW, the sensitivity is currently such that we can measure these main production modes corresponding to so-called stage 0 binning. Then in Higgs to ZZ, we can measure order of 10 bins or so, corresponding approximately to stage 1.1 granularity, and Higgs to gamma, we can go up to about 30 or so bins, corresponding approximately to stage 1.2 granularity. Okay, so coming now to the first new result. This is the Higgs to gamma with the full run 2 data set. So in this analysis, we have the signal forms a narrow peak of about 1 to 2, with a width of about 1 to 2 GeV. And the backgrounds can be readily estimated from the M gamma side bands. And compared to the previous results, we have updates to the analysis strategy. Most notably, we have new categorization that reduces uncertainties and correlations. So specifically, the uncertainties of the VH and TH are reduced by over a factor of 4 compared to the 36 impedance Ventobahn results. And with the full run 2 data set, we can also achieve increased granularity. So we can measure 27 STXS categories, and this corresponds to finite granularity specifically in the for high PT Higgs values and high MJJ values. A couple of words about the new categorization. This supersedes the legacy categorization we've been using so far, in which the categorization is processes are ordered by cross sections and then categorized sequentially. Whereas in the new categorization, we aim to just categorize all the processes simultaneously and maximize the global STXS sensitivity. And this is achieved in 2 major steps. There's the first step that just deals with the signal, and the second step that is responsible for separation of signal versus background. And the first step is composed of the multi-class BDT, which has the output discriminants for each STXS bins. And then the outputs of these discriminants are weighted, aiming to minimize the determinant of the covariance matrix of the measured yields. Then following this, in each class, we have the binary BDT separating the signal versus continuum background. And these 2 figures just show one example in processes in VBF sensitive bins for the multi-class on the left, BDT score on the right. So basically here we should look at the full region corresponding to signal compared to the dashed background. And for the binary, the signal is shown in red, and then the continuum background against which we're separating is represented by the black points, which correspond to the data segments. In terms of results, for the these are the ones for the production modes. So we have the GGF and VBF that are dominated by systematic uncertainties. GGF by background modeling, VBF by signal modeling. The other production modes are still dominated by the statistics. For VBF, we have the observed and expected significance of 7.5 and 6.1 correspondingly. For TTH, we have the observed and expected significance of 4.7 and 5. And for VH and ZH, we have this fluctuation due to which the overall compatibility of the 5 POI fit with has a relatively low p-value of 3% corresponding to 1.9 sigma deviation compared to the standard model. Now, looking into a bit more detail into WH versus ZH, what happens is that these two production modes are anti-correlated, as is seen here in the correlation matrix, and this is mainly because of the WH events with 0 reconstructed leptons populating the categories targeting the ZH. And what happens then is, if we look at the fit plot for the WH region, we see that we have a bit of an upward fluctuation here. So this pulls the WH up, and in the ZH, the WH constitutes a resonant background. So you can see here that we have this relatively large green bump from the resonant backgrounds, and this is the reason why we then fit the negative cross-section in the 5 POI fit. If we measure the WH and ZH cross-section simultaneously, we would get cross-section value that is in good agreement with the standard model with the p-value of about 50%. Now, with the full run-2 data set, we can measure about 12 bins for the GGF. The ones in the bottom here are for the high Higgs transverse momentum. The ones at the top are for the 0 jets. And further, we have the ones with 1 extra jet and 2 extra jets. Generally, the values are in good agreement with the standard model and dominated by statistical uncertainties. Then for other production modes, we can see that the bins that are sensitive to the VBF are in good agreement with the standard model. For the ones that are sensitive to WH and ZH respectively, we see again this up and down fluctuation that was evident in the 5 POI fit. And then for the TTH, we have 4 bins corresponding to different values of the transverse momentum of the Higgs. So this is the first differential TTH measurement we've produced. And for TH, the statistical uncertainties is about 300%, but nonetheless, this enables us to set the limit that the TH, or upper limit on the TH of 8 times the standard model at 95% confidence level, which supersedes our previous results on this. Okay, so now coming to the WW, where we have a new result with the full run-2 data sets for the VBF. The new measurement has high sensitivity compared to the previous publication, and this comes predominantly from the optimization of the central jet veto. Specifically, if we think about the VBF topology, in the signal, there is no jets predicted to be between these two signal jets. So if we look at the rapidity of the 2 signal jets, than the jet veto, basically VITOS events that have extra jets above some margin between the signal jets. And this veto was lifted from 20 to 30 GeV, which has two effects. It increases the signal acceptance and it reduces sensitivity to systematic uncertainties. And then also the signal to background discrimination was updated with the new multivariate discriminant. So the BDT is replaced by the deep neural network and the input variables are optimized and extended. Overall, the reduction of the systematic uncertainty compared to the 36 inverse phantom bound results is about 50%. Now, for this analysis, most backgrounds are taken from the Monte Carlo, but Z plus jets and TT bar are taken from the dedicated control regions. And for the signal discriminant, we're aiming to have it binned as finely as possible, but also requiring at least 10 signal and background events in each bin, and the background uncertainties to be smaller than 20%. So if you look at the fine print here, on the x-axis, you can see that the bin width decreases as the value of the discriminant increases. And then if we look at the high sensitivity bin, we have the signal to background ratio of about 3.5. And this enables us to extract the measured signal strength that is in good agreement with the standard model. And if we look here at the negative log likelihood plot, just look at the black curves. The full one is the observed, the dashed one is the expected one. We can see that we have the observed and expected significance over background only hypothesis of 7 and 6.5 sigma. So this corresponds to the observation of the VBF in the WWD case. The measured cross-section is in good agreement with the standard model prediction. And interestingly, this uncertainty is now with the full round 2 data set dominated by the systematic uncertainty, specifically by the VBF signal modeling. So there's strong potential for still further improvement of this with the run 2 data.
You have 2 minutes left.
Yep. Coming lastly to the Higgs to ZZ to 4 leptons. Here we are dealing with the full run 2 data sets with about 200 events with very good modeling of all the observables used for the STXX spins. For example, here I have the NJet distribution. And we have, for example, here in the invariant mass, the signal to background of about 2. The results we obtained are here shown firstly for the production modes, GGF, VBF, VH, TTH, good agreement with the standard model, p-value of 91%. And we can note that here still all of the results are dominated by the statistical uncertainties that range from 10% for GGF to over 100% for the TTH. But nonetheless, in the GGF and VBF, the 10% and 44% statistical uncertainties enable us some further interesting splitting into reduced STXX stage 1.1 granularity. Specifically, we can measure 6 GGF bins here ordered by the number of extra jets in the event and the QQ to Higgs to QQ can be separated into the bins more sensitive to VH, VBF, and BSM processes, respectively. Overall, excellent agreement with the standard model with p-value of 77%. Okay, so to conclude, for the production mode cross-sections of Higgs to bosons, we have 2 new preliminary results with the full run 2 data sets. So for Higgs to gamma-gamma, we have a detailed characterization with 27 STXX bins. Overall, good compatibility with the standard model with p-value of about 60%. For the Higgs to WW, we have an update in the VBF production mode where we have the observation with 7 observed and 6.2 expected sigma. And what's worth noting that beyond larger statistics in the full run data set results, in both cases, the increase in sensitivity also came from improvements in the machine learning discriminants and in the event selection. As for outlook, many measurements are still limited by stats. So we saw this is the case for the Higgs to ZZ and also for VH, TTH, TH measurements, as well as even finite rarity of the STXS bins. Interestingly, the VBF production mode is now limited by the systematic uncertainties of specific allocated signal modeling uncertainties. So there's still strong potential for improvement of this measurement with run-to data. Okay, that's it. Thanks.
Thanks a lot, Lisa, for the nice talk and for showing two brand new results. So we open the floor to question. Maria, first.
Yes. Okay. So first of all, congratulations for the new result. Can you go to the PBF Higgs to WW? So it's the first slide that you have. So first of all, I mean, it's a beautiful result. I was wondering if you could tell me how much. So comparing to the old sensitivity, how much does the two factors that you have added to the slide contribute? So you have the central veto and then the optimization. How much does the new optimization with the DNN matter in the improvement, and how you have extended the variables used in the DNN that you mentioned here as a leading part of the improvement?
Yeah. So how it is? I can answer better your second question, how we have extended the variables, because we have released the details for this. So let's see more, this one, okay? So basically, the previous analysis had 8 variables, and the 7 ones here at the bottom are still included, and the red one, the mass of the lepton jet, is now superseded. You go from the sum to just using the 4 individual ones. And then what you use in addition is the PTs of the 3 leading jets that give you some more sensitivity to the VBF topology. And then you use in addition also the ETMIS significance that helps you a bit with the TT bar background suppression. Okay, so this is for the first part, how we have, what we have done with the variables. Now, note also the infrastructure change. We went from the BDT to the deep neural network. Now, for separating the 2 factors, we did not release. For the 2, we did not release the numbers. What I can say that together, the central jet veto, the new discriminant, and there was also a factor that the previous analysis was struggling from the Monte Carlo uncertainties. So if you take these 3 improvements together and compare the systematic uncertainty now to systematic uncertainty there, then there is a 50% improvement. For then a specific statement on how much exactly the multivariate discriminant brings, I think it's better if someone from the analysis team could make an exact one. If need be, I can give an approximate one from my recollections from the discussions.
So maybe this is also a question that could be posted on the Mattermost, and the analyzers could answer if the informations are public, or at least to give some feeling. But maybe we could also move to the next question, since we have many, and I would kind of request if people could condense their questions and the answer a bit, since clearly there is a lot of interest for these new results. So next one is Lorenzo.
Hi, yes. So I also have a question about this measurement, actually. So I was wondering how large is the gluon fusion contribution in the VBF phase space, because I would expect it to be to have quite a large impact in the VBF measurement. And how do you separate between gluon fusion and VBF in the fit?
Yeah, so how it was for this result, the GGF was set, so for the result I quote, the GGF was set to the standard model value, but it was cross-checked by letting it float. And if we do that, then the observed and expected significance, so the observed significance would be, say, only slightly lower, about 6.3. As for the size of the GGF, I must have this in the backup slide, I think. So for the size of how many events you have, right? So in total, you have 209 versus 169. And then in the higher sensitivity, DNN bin, in which we had the signal over background 3.5, you basically have just a tiny contribution. Does it answer the question?
Okay, yes, thanks.
Just.
Okay. Next one is Weilin.
Hi, nice talk. I have a question on your slide 8 about TTH plus TH in gamma gamma.
Yep.
Okay, so here you have the measure TTH plus TH at 0.9 as central value with 0.2 uncertainty. But I remember in an early paper this year from Atlas targeting TTH production with Higgs decays diphoton only, we measured mu TTH to be 1.4 with 0.4 uncertainty. I know these two are not the same measured quantity. So I wonder, do you know what is your mu TTH here if you separate TTH from TH? Is it close to 1.4? If it's not around 1.4, do you have, I wonder what is the possible cause for a drift of central value from 1.4 to potentially something like 0.9?
Yeah, so the mu TTH in this one would be about one sigma different from the one that was measured in the dedicated paper. And the main reason should be the differences in the analysis strategy. So specifically here we do a simultaneous fit to all the production modes. Then basically the uncertainties can be pulled and constrained by other production modes. And there are some other subtle differences in the assumptions we make on the Higgs mass.
Okay, thanks.
Okay, I think last question from Ed.
Hi, I'm Ed from CMS. I had a question on the previous slide on this very nice multi-class BDT that you had. I was wondering, do you have any validation of this in a signal-like region?
So you mean something like the CMS did with the TTZ events?
Yes, something like that.
So I would say not yet, but I agree it would be an interesting thing to check. Yeah. So in the results we've published, we don't have such check as you had.
Okay, thanks.
Okay, so thanks a lot for the many questions. I think that we can probably move on to the next talk. Unfortunately, this is the course of showing new results at the conference, but it's a prize that we're very happy to take. So next one is from, so we now move to non-bosonic final state. And Daniel?
Hi, can you hear me?
Yes, we can hear you. We can see you.
Okay, I'll just share the slides.
Okay, I can see the slide, but not in full screen mode.
Right, okay, should be full screen
Okay, now it's full screen, so please start when ready.
Okay, hello. Today I'll be presenting the latest Higgs boson measurements in final states with TAUs on behalf of the CMS collaboration. So first, just to give a quick overview of the slide contents, I'll start just giving a general introduction to standard model Higgs tau analyses, which will cover common elements in the two main analyses I'll present today. I'll then show the latest cross-section measurements. And finally, I'll present for the first time measurements of the CP properties of the Higgs tau decay process. Okay, so there's many motivations why we want to look at Higgs tau decays. So first of all, of course, it's a way to directly probe the Yukawa coupling to tau leptons. However, we're also sensitive to different couplings via the various production modes. And in general, because it has quite a high branching ratio, it's able to probe regions of phase space that tend to be less populated, like VBF-like regions or boosted Higgs topologies. Although this final state isn't without its challenges, and those mainly arise because taus themselves are unstable and decay inside the beam pipe very close to the primary vertex to either leptons or hadrons. But in both cases, we always have some undetectable neutrinos in the final state, meaning we can never reconstruct the Higgs system exactly. So in the analysis presented today, we split events depending on how the two towers decay into 4 channels, 1 leptonic channel, 2 semi-leptonic channels, and all hadronic channel. Throughout the slides, I'll use this notation to denote the hadronically decaying taus as well. And you can also see a nice example of an event display here of a semi-leptonic event where we have a muon and a hadronic tau in the final state. Okay, so of course, important to this analysis, being able to identify properly our tau decay products. In the leptonically decaying tau leptons, the electrons and muons that are produced are very similar to prompt electrons and muons, so we just use quite standard electron and muon identification. For hadronic tau identification, this starts with the hadron plus strips algorithm. This basically identifies charged hadrons plus clusters of E gamma deposits from pi0 decays, which are clustered into strips. The resulting tau candidates from the HBS still have quite a large background from jets and lepton fakes, so we reduce these using a multi-class deep neural net algorithm called deep tau. What's quite nice about deep tau is it shows a significant performance improvement over the older BDT-based IDs, as illustrated in the plot on the slide. You can see the ROC curve for deep tau in blue compared to the older BDT in green, showing a clear improvement. Okay, so in terms of backgrounds, our largest background tends to be from Z-tau events. This background process we estimated from a data-driven method called the embedding method. The basic idea of this is that we select Z-mu events in data, which due to lepton universality have very similar kinematics to the Z-tau process. We then remove the hits from the muons from the data and replace them with simulated tau leptons. Our second largest background is due to jets faking hadronic taus, which again is estimated from a data-driven method called the Fay rate method. Basically, this is just using anti-isolated data scaled by some weighting factors to estimate properly the signal region. And then the remaining backgrounds are all estimated from Monte Carlo, and total only 10% of the total. Okay, so moving on to the latest cross-section measurements. So basically, with the full run-2 data set, we're now able to make much more precise measurements of Higgs boson cross-sections. So this includes both inclusive cross-sections of different production processes like gluon fusion and VBF, but also allows us to make more differential type measurements such as the SGXS framework, which we've already heard about today. Okay, so for the analysis strategy, we target the most sensitive, 4 most sensitive channels I already outlined on the previous slide. We then split events into categories, first of all, to target different production processes. To have a zero jet category targeting mainly GGH events, a VBF category requiring 2 jets plus some additional high invariant mass or delta eta requirements to pick up VBF events, and then a boosted category, which basically contains everything else. We then further subdivide the categories to target specific SGXS bins. So this is using equivalent RICO level variables that are used to define the SGXS categories, for example, NJets or Higgs PT. And then to extract the results, we fit 2D discriminants, where one dimension of this discriminant is always the ditau mass, which tends to give the best separation between signal and background. And then the second variable, we choose both to give additional separation between signal and background, but also to align with specific SGXS bins. So in this plot, you can see an example of a 2D discriminant of the dijet invariant mass shown with windows indicated by the dashed lines versus the ditau mass. Okay, so moving first on to the inclusive cross-section results. These are extracted by means of a simultaneous bin maximum likelihood fit. For the inclusive Higgs production, we've currently measured a best fit value of the cross-section of 0.85 times the standard model expectation, with an uncertainty of about 0.12. And we've also measured the cross-sections for the individual production processes, GGH measured to be about 1, and QQH measured to be about 0.7. To help illustrate the results as well, we also produce this weighted dye-tau invariant mass plots. This is combining together all channels and categories weighted by S over P. And you can see here the signal shown in red on top of quite a large background. But once we subtract the background contribution, we can see clearly a nice peak around 125 GeV. The results are also interpreted in terms of coupling modifiers. This is done in two ways. So first of all, we assume we assume signal strength modifiers for the GGH and VBF process and produce a 2D scan. And in the second interpretation, we assume there's a common coupling modifier for the coupling of Higgs to fermions and the coupling to weak gauge bosons. And you can see the 2D scan for this assumption as well. So the STXS cross-section measurements, as a few analyses have said already today, it's not always possible to measure every single STX bin. The reason is we have quite strong correlations between neighboring bins in some cases. And we can also have unreasonably large uncertainties which don't really warrant a specific measurement. So what we do is we apply some merging together of the categories. The first type of merging, first merging scheme we apply is called the process-based merging. So in this scheme, we basically leave GGH and VBF as separate processes as they are in the standard STXS setup, and we then instead merge together neighboring STXS bins. And you can see the results of both the absolute cross-section measurements in the left-hand side and relative to the standard model expectations in the right-hand side. And all these agree quite well with the standard model predictions given the uncertainties. And the second merging scheme we use is so-called topology-based. So here we merge together GGH and QQH using just a common signal strength modifier in categories where we have large VBF expected. So the reason is just that the GGH always contaminates these QQH regions and they're quite difficult to disentangle. So we just tie them together and they're shown in green on the plots. Okay, so this brings me on to the final part of the slides today, where I'll present for the first time measurements of the CP properties of the Higgs tau decay process. So you might be aware there's quite a long history of CP measurements by both CMS and Atlas, but these are mainly focused on the couplings to weak gauge bosons. However, the fermionic couplings are much less tested, and actually many models are more well motivated, seeing as we can get CP odd couplings to fermions already at tree level compared to loop level for the couplings to weak gauge bosons. There are some measurements of the TTH process already by CMS and Atlas, but as of yet, there was no measurement of the couplings to tau leptons. So just on this slide, I'll also define the parameterization I'll use throughout the rest of the slides. So starting from the Lagrangian describing the Yukawa interaction, you can see there's two terms. This first term, proportional to kappa tau, which is a reduced Yukawa coupling, describes the coupling to the CP even component. And then you have the second term, proportional to kappa tau tilde, describing the coupling to CP odd component. For convenience, we define effective mixing angle phi tau tau, defined as the arctan of the ratio of the two couplings. And basically this tells us the CP nature of the Higgs coupling to taus, with a 0-degree angle corresponding to a CP even Higgs. CP odd would be 90 degrees, or a mixed CP scenario would be any intermediate values. Okay, so ideally how we would like to reconstruct phi tau tau, if we could reconstruct the Higgs and tau systems fully, is we'd like to take the angle between the two tau decay planes and the Higgs rest frame. And this would have a differential distribution as shown in this plot. You can see a characteristic sinusoidal type shape, where a phase shift in this distribution is related to the value of phi tau tau. However, due to the missing momentum from the neutrinos, we can never reconstruct the Higgs system exactly. Neither can we reconstruct well the tau system. So we have to rely on approximate methods for the reconstruction of the decay planes. These can kind of be grouped together into two main methods. The first one concerns cases where we have an intermediate resonance. So the best example of this is a tau decay to rho meson, which is actually the highest branching of all tau decays. And this rho meson then subsequently decays to a charged and neutral pion. So in this case, we define our decay plane based on these two visible decay products as shown in the middle illustration here. And then the second thing we can do in cases where we don't have an intermediate resonance, we can still define a decay plane using what's called the impact parameter. So this is denoted lambda in the plots, and basically what it is the vector pointing from the primary vertex to the point of closest approach on the track. So in this case, the plane is spanned by the visible tau decay products and the impact parameter. And again, we take the angle between the two to be sensitive to CP. The current analysis targets the most sensitive final states, so one semi-leptonic channel with a muon and a hadronic tau, or the channel with two hadronic taus. And in general, we consider all the sensitive hadronic tau decays, which gives many channels in the final combination, but the most sensitive three tend to be the free channels here. So with a muon and a rho in the final state, with two rhos in the final state, or a pi and a rho in the final state. Okay, so for the analysis strategy, of course, we also need to be able to separate signal from background efficiency to give us good sensitivity. So this is done by means of a BDT or neural net multi-class method, depending on the channel. And this includes kind of common kinematic variables like masses and PTs. This is multi-class, so we have two background categories, a genuine tau category and a fake tau category, and then just a single signal category, which merges together different Higgs production processes, seeing as we don't need to be able to separate these well to measure the CP properties of the decay vertex. And then we extract our results by fitting 2D discriminants again. In this case, the 2D discriminant is formed from the MVA score versus phi CP. So in the example here, you can see these dashed lines indicating different MVA score windows. Within each of these windows, we bin in phi CP, and again, you can see quite a characteristic sinusoidal type shape for the signal on top of quite a flat background. Okay, so this brings me on to the results. So once again, we extract the results by maximum likelihood fits. And you can see the delta log likelihood scan that was observed in data shown in the red curve on the left-hand side. And this can be compared to the expected with the blue dashed lines. So the best fit value extracted from this curve is 4 degrees of phi tau tau plus or minus 17 degrees. So this is consistent within one standard deviation from the standard model expectation, which is 0 degrees. And it should be noted here that when we break down the uncertainty, it's almost entirely statistically dominated at the moment. Okay, and we can also interpret this in terms of the two kappa tau parameters if we make some additional assumptions about the other Higgs couplings. So in this case, we assume all of the Higgs couplings are standard model like. And you can see then the 2D scan of the two kappa terms with the standard model expectation shown in red, agreeing within the 1 sigma region.
You have 3 minutes.
Okay, thank you. So to help illustrate the results better, we also produce a similar S over B type weighted distribution. So in this case, rather than looking at the di tau mass, we look at the phi CP observable, and we combine together just the 3 most sensitive channels that I outlined already on the previous slide. So in this case, we do a double weighting. So first we weight by S over S plus B, as is kind of done usually, but then we also weight by this additional factor A, which is, we call the average asymmetry. So what this is basically telling us how much separation do we have between CP even and CP odd in each category. So it's defined by taking the difference between the two hypotheses in each bin divided by their average and then averaging over all bins. And it's worth noting as well that the mu rho channel has to be phase shifted by 180 degrees for this distribution, just so that the peaks line up with the other two channels. So when we weight the data, we then subtract the background contribution and we observe the resulting data points. What's quite nice here is you can see these clearly favor the CP even hypothesis shown in the solid blue line and disfavor the CP odd shown in the green line. And actually the CP odd here is excluded at level of 3.2 sigmas in the observed compared to 3.2 sigmas that were expected. Okay, so this brings me on to my conclusion slide. I presented today the latest results of the inclusive cross-section measurements and SGXS measurements in the di tau final state. The inclusive cross-section was measured to be 0.85 times standard model expectation with an uncertainty of about 0.12. And I've also presented for the first time the measurement of the CP properties of the Higgs tau-tau decay coupling, which we parameterized in terms of an effective mixing angle, which was determined to be 4 plus or minus 17 degrees. With the CP odd hypothesis excluded at a level of 3.2 sigma. Thank you for your attention.
Thanks a lot for the nice talk, and again, more new results, which is amazing. Question time, I think we can start from Christian.
Yeah, hi, this is Christian from Atlas. Yeah, thanks a lot for the nice talk and congratulations to the nice result, especially on the CP properties. So yeah, on the CP properties, can you maybe say a few words? Have you studied how much you're affected by uncertainties of the of the directions on the tau decay products, because I think this should have a big impact on also on the angular difference between the tau decay planes in the end.
Yes. So what we're basically seeing is that we're not very sensitive to the uncertainties on the angular decay products. So the way we validate this is we look at I'll just skip to one of my backup slides. So we can validate the description using Z tau events. So usually these have a flat distribution, at least at gen level. But this is paper by Stefan Berg et al., where they define a parameter alpha minus, which can be used to split your flat events into two sinusoidal-like contributions. So this is splitting alpha greater than pi over 4, alpha less than pi over 4. And what we see when we compare data to the Monte Carlo prediction of Z tau is we have very good agreement. So we conclude we're not sensitive to the angular, the uncertainties on the angular resolutions.
Thanks.
Okay, thanks. Maybe time for one very quick question, if there is. Okay, does it seem so? So thanks again, Daniel, and we go to the complementary talk from Atlas. From Christian.
I guess you can hear me.
I can see you, I can hear you, and now I can see the slide. If you can go full screen.
Okay, yes.
Okay, yes, please start when ready.
Yeah, thanks a lot. So yeah, my name is Christian Grefe from the University of Bonn, and it's my pleasure to present you the Atlas results on Higgs to tau tau. And so we have so far only published results on the early run-2 data set, so that's 36 in the Femtobahn from 2015 and 2016. And so the two measurements I will discuss is first of all, it's the measurement of the cross-section for Higgs decaying into 2 taus. And then based on this analysis, a test of the CP invariance in vector boson fusion. So this, unlike the previous talk, which focuses on the Yukawa part of the Lagrangian, this is looking into the coupling to the vector bosons. Okay, on slide 3, just for the motivation, so you've all seen this already many times. So of course we want to test first of all that the Yukawa coupling is indeed as predicted by the standard model, so that we have this nice correlation between mass and coupling to the Higgs boson or the branching ratio. And so this is a very important test of the standard model. And okay, so far the tau leptons are the only leptons where we can test this correlation. Okay, this is maybe slightly outdated since we've seen the nice new results from CMS on Higgs to mu mu with the first evidence of this decay as well. And then, but yeah, as already mentioned by the previous speaker, since Higgs to tau tau has a quite sizable branching ratio, as you can see on the top left, as compared to, for example, to Higgs to gamma gamma and others, you can actually have quite a lot of statistics where you can plot different production modes and also investigate the CP structure, as I will discuss further. Okay, so the leading production modes at the LHC and proton-proton collisions for the Higgs is of course the gluon fusion, here shown in blue, and then followed by VBF about 1 order of magnitude below in red. And then you have also the production modes with VH and TTH production. And with this 36 inverse Femtobahn, we are only really sensitive to the leading two production modes. So I will focus on those. So that's gluon fusion and vector boson fusion. So on slide 5, so for the measurement of the cross section, in Atlas we select any combination of good leptons. So that means electrons, muons, and hadronic taus, and these we then label as 3 analysis channels. So we have a lepton-lepton channel, a lepton-hadron channel, and a hadron-hadron channel. And so where the last two ones are the most sensitive ones. And then in addition, we do have separate categories to target vector boson fusion, where we have 2 additional jets that are very forward, and or at least one high PT jet, which we then call a boosted category, and that's mostly gluon fusion production processes. And then to maximize the sensitivity, we have additional subcategories that use primarily the dijet mass for the VBF category and the PT of the ditau system, or PT Higgs in this case, to maximize the sensitivity. And so these in total give us then 13 signal regions that are used in the fit. And the key observable that we need to separate the Higgs to tau tau from the most important background, which is Z to tau tau, is the ditau invariant mass. And because of the neutrinos in the tau decays, this is of course not completely reconstructed with our detector. So what we use is a so-called missing mass calculator, which is a likelihood estimator of this ditau mass, which takes the reconstructed taus, being lepton or hadronic taus, and the missing energy, and then combines this. And you can see on the right side, this is just showing the shapes in blue for Z to tau tau and in red for Higgs to tau tau. And you can see that they are nicely separated, and you can also see the lines split for the different tau decay modes. And the most important part here is not actually the precise position of the peaks, although they are quite nicely where you would expect them at 90 and 125. But the key part is, of course, here the separation between the 2 peaks to distinguish signal from background. So here on slide 6, you can see some example event displays that for the 2 categories that I just mentioned. So on the top left, you can see a nice event where we have an electron and an hadronic tau reconstructed in 2 very forward jets. So this is one of our candidate events in the Leopard BBF category. And on the bottom right, you can see an event display with a high PT jet, and then recoiling against this 2 hadronic taus. And you can also see the transverse view with the missing energy in between. And yeah, this is a candidate for the boosted category. So moving on to the most important backgrounds. So here in this chart on the bottom, you can see on the left side the 2 columns. These are from the lab channel, and the middle 2 columns are from the lab-HUD channel, and on the right side it's the HUD channel. And from so on the bottom you can see the signal regions, and on the top there are the control regions that we use in the fit. And so first of all, you can realize that in the signal regions, we are, of course, as expected, dominated by the blue contribution from Z to tau tau, which we estimate using Sherpa. And then we validated this in a corresponding DLL region. And then for the other backgrounds, like TT bar, which is also estimated from Monte Carlo, we have control regions where we can control shapes and normalization. And especially in the lab channel with same flavor leptons, we have important contributions from Z2LL, and this we also control in a dedicated control region. What's also very important is the yellow contribution, and this is misidentified taus. So and then, of course, depending on the final state, this is either lepton fakes or hadronic tau fakes. And so, especially in the lab-HUD and HUD channel, these are very important. And so in lab-HUD, we estimate this using a fake vector method where we invert the tau ID, and then that's how we get the estimate for this contribution in the signal region. And in the HUD channel, we do this by inverting the charge requirement. So going from a from an opposite sign requirement to a not opposite sign requirement. All right, so moving on to the result on slide 8. So on the top left, you can see the nice plot with the combination of these 13 signal regions weighted by the S over B. And you can nicely see the peak at 125. So in this combined likelihood fit with all the control regions and the signal regions, we get then an observed significance of 4.4 sigma. And then if we combine this with the 1-1 data, we even get 6.4 sigma. So that's an observation. And you on the right, you can see these numbers as total cross sections for cross sections times branching ratio to Higgs to tau tau. In combination, which is slightly higher than the standard model expectation, so 1.09, but still consistent with the standard model. But then if we do the measurement in the three channels separately, we can see a consistent picture, also consistent more or less within 1 sigma with the standard model expectation. And also if we do the fit in the individual categories, so this is not the VBF cross-section, but really meaning the total cross-section extrapolated from the VBF category here, just to avoid confusion. All of this is all consistent with the standard model expectation. And then on slide 9, you can see that we've also done a measurement with more parameters of interest. So instead of measuring the total cross-section, we then measured separately P1 fusion and VBF cross-section times 60 tau tau branching ratio. And on the left, you can see the correlation or the ellipse from this measurement. And so the best fit value is here indicated by this blue star. It's very close to the standard model expectation. And you can also see the limits here, which are all very consistent with the standard model expectation. And this is then, of course, input to our Atlas-Higgs combination, where you will see an update later today for this. And since we had already these subcategories that are binned in Higgs PT, essentially, this can easily be translated to a fiducial cross-section measurement, or rather SDXS stage 1 is just 3 bins, but nevertheless. And you can see that this process is especially sensitive to the high PT regime, where we get very good sensitivity, as well as the VBF topology. So this motivates that we can use this channel to also look at possible CP violation in vector boson fusion coupling to the Higgs, which you could do with other decay modes as well. But so the general ansatz is usually to write the effective Lagrangian, and here we only include the CP odd operators of dimension 6. And then this is some choice. We parameterize this just in the 2 parameters d tilde and d tilde b, and then you can write out the coupling terms like is shown here on the slide. And then since we only are interested to test if there's CP violation or not, we actually don't care about the concrete coupling parameters. We do the arbitrary choice that we do set these 2 d tilde values to equal, and then it simplifies further, and we just have one simple dependency here for this for these couplings. And so if you write them down, the matrix element squared, you can get the CP even contribution from the standard model, then some mixed term where you have the CP, which is CP odd, and then also a CP even contribution that changes the rate from the CP odd addition to the standard model Lagrangian. And with this, you can construct a so-called optimal observable, which is just checking if there's CP violation or not. And you can see this on the right in black. This is the standard model hypothesis, where we have a d tilde value of 0. And if you modify the d tilde value, you shift this distribution left and right. So what we test is, we plot this observable, and then we test if it's symmetric around 0. So in practice, how did we do this? So yes, so first of all, you need to reconstruct the matrix element, and we use half for this. And so we take the reconstructed form momenta of the Higgs using the MMC as discussed before, and the reconstructed jets, and then we can use this in our signal region to extract possible or limits on detail. And in principle,
you have 2 minutes.
Yeah, sorry. Okay, I will speed up. So this would work with any decay mode, but since we have very high sensitivity for VBF and good form momentum resolution for Higgs to tau tau, this is very nice for this channel specifically. So what we did to get even higher signal purity than in the coupling measurement is we introduced the BDT, where you can see this nice signal background ratio on the bottom. And the low BDT score region is still used in the fit to constrain the background. So on the next slide, you can see some example plots. So this will use di-tau mass region for the low BDT region and optimal observable in the high BDT region. And you can see that we have very good signal over background ratio. And on the bottom left, you can see that if you just look at the data, that everything is consistent with 0. So no CP violation, unfortunately, observed. And then on slide 13, this is then the resulting limits. So if you try multiple detailed hypotheses, you get to the plot on the bottom left, where you have the different colors of different decay channels, but the black curve is a combined result. And so this is unfortunately only, we only reach a 68% confidence level limit between 0.09 and plus 0.035. And the main reason for that, as you can see in the middle plot, is that we have, with this selection, unfortunately, a slightly lower than expected signal strength. So if we had a signal strength around 1, then the limit would be much stronger. But okay, this is what the fit gave us. And yeah, in general, this is all limited mostly by statistics, of course, but also by jet uncertainties. So to summarize. So as you've seen, we have the observation Higgs tau as seen in Atlas with already with the early run 2 data. We've measured cross sections in VBF and gluon fusion and reduced the VBF production process to put limits on CP violation using this detailed parameterization. And so far, everything is consistent with the standard model expectation. And we're obviously looking forward to look at the full run data set as well. And just to mention that in addition to more statistics, there's also other developments in Atlas. So one example here is that there's a new tau identification algorithm, which we've published. And so this is not yet used in the analysis that I've shown you here, but what you can see is that you move from the dashed line, which is our previous tau identification, to the full lines, and you get basically twice the background rejection for the same signal efficiency. So that should be a very nice increase of the sensitivity in the future. And I should also mention that there is a poster on this later today that you're welcome to watch. Okay, thanks.
Okay, thanks a lot, Christian. We are running a bit late, so we might have time only for one question. Daniel?
Hi, thanks for the nice talk. I was just wondering, when you fit the VBF CP properties, what do you do about the gluon fusion background? Do you assume it's standard model, or do you float the CP in the top coupling, for example?
Let me think. I think we left it floating, but I would have to double check. This is, yeah. But it's a very small contribution after this BDT selection.
Right. Okay. Thanks.
Okay. So unless there are really urgent questions, doesn't seem to be the case. So thanks a lot, Christian. And we go to the last talk of the session from Sergio.
Hi, can you hear me and see me?
I can hear you. I can see you.
Okay, let me share my slides. Just 1 second. Okay.
And I can see your Skype. Oh, now I can see your slides. And if you can go full screen.
Yeah. Okay, you should have it now.
Yes, please start when ready.
Okay, thank you. So I'm going to present the latest results on TTH and TH associated production measurements at CMS. So, well, just a brief introduction first. So as you know, TTH and TH are one of the few direct probes to the top Higgs Yukawa interaction. The measuring this process essentially allows you to measure both the strength of the Yukawa coupling, but also allows to, for instance, probe for CP violation in this sector. But still, measuring this process it's quite challenging. For instance, the cross section of TTH, sorry, it's a half a picobarn, so it's quite challenging to do so in the LHC. It also yields to quite rich topologies due to different Higgs decays and top decay modes. TH it's even more challenging than TTH because its production cross section it's even smaller, but it has the nice feature that on top of these diagrams that contribute with the Higgs top Yukawa coupling, it has also diagrams with the W Higgs coupling. And essentially the interference between these two is destructive at the in the standard model, but in the cases in which essentially the coupling of one of these two is negative, or has the opposite sign as the standard model, then this enhances the DH cross-section by a factor of 10 roughly, but doesn't have any effect on the DH cross-section. So this means that well, it's interesting to study this process. So this can be studied in different channels, depending, of course, on the decay modes on the Higgs. And in fact, we already reported an observation of these processes when considering all the decay modes. The main one of them are the well, starting from the BB bar. This has the largest branching ratio, but it also has large backgrounds. And then the two ones that I'm going to cover in this presentation are the gamma gamma. Well, this final state is very interesting, as you saw in Huilin's talk. It has very low background and also quite low branching ratio, so it's challenging. But it has the nice feature that allows to reconstruct the Higgs system. And then what we call the multi-lepton final states that are essentially putting together WWCC and tau decay modes. They have it's also quite interesting result and channel because it has moderate background, but also it has quite significant branching ratio. So I'm going to cover these two talks, and in fact, the result on TTH multi-lepton is presented for the first time in a conference here. These are performed with the full RAN2 dataset. They are the legacy results of CMS and are obtained using 137 index femtogram of data. So starting with the diphoton search. So essentially, this analysis is done by well, using events with two photons and having different categories targeting the hadronic or leptonic top quark decays. Here, the main backgrounds are essentially TT bar plus gamma, and here we use PDTs that have several inputs as background. Then we have a signal and background model that we use to feed the gamma gamma distribution in each one of the categories separately. With this, we obtain a signal strength of roughly 1.4 plus minus roughly 30. And this leads us to an observed significance of 6.6 sigma with respect to the no TTH hypothesis. This channel also allows to study CP violation, and this we have done in the same result, but you can find more details in Saba's talks on this. Okay, so I move on to the multi-lepton search, which is the new search that we are covering here. So this search is performed by using data in 10 different categories that are defined based on the lepton and hadronic tau multiplicity, and each one of them targets a specific decay of the Higgs boson and of the top quarks. So also on top of this selection, we also apply cuts on lepton charge in order for them to be consistent with the expected final state, and also on the jet multiplicity. But the new feature that we have added in this incarnation of the analysis is that in the most sensitive regions, which are the 2 leptons inside 0 tau and 1 tau, and 3 leptons plus 0 tau, we have a large surface space to also accept the TH events. So essentially, we allow events with one B jet and also an additional jet that can be forward. So we accept, so we have sensitivity to the TH reproduction because the expectator quark can be forward. Additionally, we also have control regions with 3 and 4 leptons, out of which one is a set boson candidate that we use to constrain the TTC background. Then, as you saw in the plot in the previous slide, these signal regions are still fully dominated by background. So we make use of MPA discriminators that we use to separate signal from the various backgrounds. As input variables, they take essentially the 3 momenta of jets, leptons, and hadronic taus of each category. And also, well, simple variables like invariant masses, angular distances among objects, and object multiplicities, and also specific taggers that allow us to identify decay products of the top quarks and Higgs boson. Then we have a twofold strategy. So in the most sensitive regions, the one that we also use for TTH measurement, TH measurement, we have moved through an approach in which we would have 2 VDTs discriminating the different species of backgrounds. to a more advanced approach that makes use of a multi-class DNNs and allow us to discriminate TTH, TH, and the different backgrounds separately, but in the same, in the same setup. Then we are able to build categories based on the species of each one of the processes and on the topology. This I will show more specifically in the next slide. For the rest of the regions, we don't expect sensitivity for TH production, so we make use of a VTT discriminator, just training TTH against the backgrounds. Okay, so here I have one slide on what we do in these three more sensitive regions, that the ones that make use of multi-classifiers. So essentially, these multi-classifiers allow us to classify events in each region as TTH-like, THQ-like. In the case of the 2 leptons in sign, TTW-like and other backgrounds. In the case of the 3 leptons plus 0 tau and 2 leptons in sign plus 1 tau is the same, but we don't have TTW. And then we also further classify according to the topology of the event. So essentially, we have the lepton flavor, the Bijet multiplicity, and the same in the 3 leptons plus 0 tau region. Additionally, on top of this, we also classify based on the score of the DNN of the most probable process. So in the TTH category, for instance, we classify also based on the probability of an event being TTH. Moving on to backgrounds. Backgrounds are also crucial in our analysis because, as you saw, we are quite dominated by them in the signal regions. So we have two types of background, which are reducible and irreducible. For reducible backgrounds, these are dominated by non-prom leptons and misidentified taus and electron charge flips, for which we use background estimation methods. Data-driven estimation methods. Also, we have a small contribution from photon conversions that we also estimate from simulations. Irreducible backgrounds are dominated mostly by TTC and TTW. Also, although we have other contributions from rarer processes. And then, while TT bar and Drell-Yan also become irreducible in some of the categories. For all of this, we have estimated them using state-of-the-art Monte Carlo simulations, and are either normalized to the most precise theory calculations or are left freely floating in the signal extraction fit. So we don't really make an assumption on the cross-section value. So I start describing a bit further the reducible backgrounds. So for the main contribution from them it's really non-prom leptons, and for this we have really pushed the capabilities of our detector and our lepton reconstruction algorithms to build an IMVA that essentially allows us to discriminate between prompt and non-prompt leptons. This makes use of isolation variables, input parameters, and also beta-gain algorithms. For instance, we are using the DeepJet algorithm developed within CMS. And we are able to very much discriminate them. Still, a tiny portion of it goes into our signal regions, and essentially here we are using the canonical approach of using the Titulus method, deriving a transfer factor in multi-jet events. Here in these two plots, you can see the consistency check of the method in TT-bar simulations in one of the signal regions, and you see that it works very good for muons. It works respectively good for electrons. And then, well, a couple of words on electron flips, which is the other main background, reducible background, that has a small contribution, and essentially this is estimated in a opposite sign sideband, and we essentially derive a transfer factor in a Drell-Yan control region. Then moving on to irreducible backgrounds. So, well, first to say that I speak a bit about the normalization. So the TTC and TTW normalization are fully determined in the signal extraction fit. It's a free parameter, so we don't really make an assumption on the total cross section. For TTC, we have specific control regions which are the ones that you see in the top right and in the bottom right with 3 and 4 leptons respectively, with a set candidate. And well, essentially this allows us to discriminate very well or construct very well TTW background. Sorry, TTC background. For TTW, we don't have a specific signal region, but control region, but we have a TTW category in the 2 leptons in sign plus 0 tau that we build with the DNN score, and you will see it's quite pure in TTW. So on the shape, so TTC and TTH are simulated at next to leading order in QCD. TH is simulated at leading order. And TTW, as you all know, it's a bit more challenging because there are non-trivial corrections to the standard NLO QCD and also standard electroweak corrections. And with this, we have reached out to the theory community, and we have implemented the most accurate calculation available at the moment. So essentially, we are using NLO QCD, including this LO1 and NLO21 terms, but additionally including this alpha cube and alpha cube corrections in the generator with MCAT NLO. So essentially, we are using the most advanced calculations available at the moment. So I move on to the results. These are the yields in some of the most important categories. You see that overall there's a good agreement with data and the model and the fitting model. Also, you should see that in the regions in which we expect to be more enriched in TTH, there's a clear presence of TTH, which are these three. And also you see that the TTW background the selection, as I was saying before, it's very pure. So this allows us to constrain very well the TTW background. Then I move on to the signal extraction, which we make by performing a likelihood fit to all of the categories in the analysis that you can see summarized in this SOVR plot. And this analysis allows us to have a sensitivity of 5.2 sigma and a sensitivity to TTH production of 0.3 sigma. The measured signal strength for TTH is 0.92 plus roughly 25%. And you can see that it's quite consistent across all of the categories. Then here I also have the signal strength for TH, which is 5.7 plus minus 4. TTC is also consistent with the standard model expectation, and TTW is still above the expectation. We have 1.4 plus minus 20%. All these signal strengths, the leading systematic uncertainty, except for TH, is the theory calculation on the respective process. So if one was to measure the cross section on this, of course the uncertainties will decrease significantly, especially for TTC.
You have 2 minutes left.
Okay, thank you. So here I show the combined extraction of the TTH and TH. Essentially, you see that is consistent within the standard model expectations. And here, well, you see the TH measurement per categories, or per sensitive categories. The observed significance for TTH production is 4.7 sigma, and for TH production is 1.4 sigma. Then what we have done is to interpret these results in terms of modifiers of the top and WC Higgs couplings. We take into account their effect on the TH kinematics and also on the Higgs boson branching fractions. And what we do is to compare the compatibility of our data with different hypotheses of kappa T and kappa B, building a scan on these two parameters. And essentially, this allows us to build credible regions in the 2D plane of kappa B and kappa T that you see here, and you see that we are consistent with the standard model. And then, well, as a function of kappa T, essentially, this allows us to constrain kappa T between these two intervals, so between minus 0.9 and minus 0.7 and 0.7 and 1.1 at 95 confidence level. So, okay, with this, I'm finishing. So I've covered TTH and TH production with the full run-through data set. This has led to an observation of TTH production in the diphoton channel, and also to more than 5 sigma sensitivity or to TTH production. And well, there you have the measured signal strength for each one of the process, and also the expected and observed significance. And just to mention that this also allows to constrain Higgs coupling modifiers in a very constrainable way. So thank you for your attention.
Thanks a lot for the nice result. So this nicely closes our session. So time for questions. We can take a few. Tamara.
Hi, thanks a lot for presenting this new multi-lepton result. I had some questions. You can stop me if there are too many.
Let's start with one.
Let's start with one. Maybe on the TTW normalization factor that you measure, I think on slide 12. you mentioned before that now you're including within, for the benchmark of your TTW calculation, the electroweak corrections. But in the case from Atlas, we were also considering, for example, the missing higher order QCD corrections like +1 jet at NLO. So to be able to compare this number with what we obtain, is this included as well in the benchmark? Or
no, this is not included. It only includes the...
Okay. Then the other question I had, if I still may, you show these very nice also plots for the non-prompt lepton estimation on slide 9. And I wanted to maybe understand a bit better at the top right-hand side. Are these the transfer factors that then you correct, that you use to correct when you extrapolate from the multi-jet region to your signal region? Because
this essentially, this is the comparison of the so essentially we take TT bar Monte Carlo in the signal region, and essentially this is what you get in the gray nominal one, and then we essentially apply this Taitulus method with transfer factors derived in TT jets and multi-jet simulated events, and essentially we compare the three. So if essentially you want red to agree with gray more or less, and you see that they agree quite well. So they are yields essentially.
Right, because for electrons at low PT, you have at around over 50%.
Yes, this we take into account as actually we correct for this difference, and we also take this into account as a systematic uncertainty.
Okay, thanks a lot. I have one more, but maybe I'll let other people
let's
talk.
So Lisa?
Yeah, in fact, it's pretty much almost the same question as Tamara's asked about TTW normalization, but more concrete. So we used to normalize it to the prediction from Yellow Report 4. So how different this current normalization from the number you used before? It's important to know because in the latest for top analysis, which uses the same final state, we see the same, 1.6 for TTW, but we normalized to Yellow Report 4.
Yeah, so if you want concrete numbers, it's about a 10%, but if you want the concrete numbers, this is going to be released in the public document.
Okay, no, 10% is good enough for me, so it's not 20%.
No, I think not.
Okay, thank you, but it's still consistent with what we're seeing. Thanks.
Okay, is there anybody for a question, or maybe we can give the microphone back to Tamara? So, okay, Tamara, you have one more.
Okay, thanks a lot. On slide 11, this is more out of curiosity. You show for the first plot for 2 lepton Simpson 0 tau, the signal region for TTH. There seems to be some type of excess at more background-like pins. So these first pins for mu mu. Yes, I don't know if you maybe took a look a bit deeper to try to understand this in terms of actual, patterns in the phase space.
No, we don't have any indication that this is more than a statistical factorization.
Okay. Okay, thanks a lot.
Thank you.
Okay, I assume that Lisa has a follow-up, or you didn't?
Well, it's almost on the same thing, but
okay.
Can you please, maybe I missed, describe other systematics on TTW you apply?
Sorry, what? So you mean, for instance, just we apply the usual systematic uncertainties in PDF?
Floating in the fit, but there must be other systematic uncertainties.
Yeah, we have on top of the experimental uncertainties, we also have the usual theory systematics on.
But what is usually theory systematics? Can you please?
Yeah. So we take into account the variations of the renormalization and factorization scales.
Right, but your main sample is what, Sherpa?
No, it's MZ and low.
MZ and low, but you don't compare it with anything else.
No.
Thanks.
Okay, time for a very, very last burning questions. Otherwise, I would remind you that there is still the Mattermost channel that could be used to ask questions as an example for this chat. So I don't see any, and so we can go in coffee break mode. And thanks again, all the speakers, for this extremely interesting session full of new results. Maybe before that, Thomas, you want to give some practical information?
Okay, thanks, Valerio. Well, we reconvene at 10:54 sharp as originally planned, because we cannot. We still want to have some contingency time between the end of the next session and the poster session. That's the reason. So the coffee break will be a bit shorter, but still, I think it's sufficient.
Okay, so see you everybody in 20 minutes or so, a bit less.
And meanwhile, if there is someone willing to test audio or screen sharing, is welcome to do so. Okay, hello again. So if we still have a few minutes before we start, so if anyone wants to test audio or slide sharing, please do so.
Yes, I'd like to do it. I'm Nasir Osei. I have a talk at the end of the session. Okay, can you hear me?
Yeah, perfect.
Okay, and I think that there's no problem with the video. One moment. Exactly,
Yeah.
I think that the video was properly. So then I am going to share the. May I share the screen now?
Sure.
Yes. So then I think that. Yes, I have here the PowerPoint.
Just make it full screen. Yes, perfect. Yeah.
Yes, I think that it works perfect.
Okay, perfect.
Okay, perfect. Okay, so then thank you. I'm going to close.
Okay. You're
Okay,
welcome.
thank you.
You're welcome.
I may also try to test.
Sure. Go ahead.
So do you see my slides?
Yes. Just make it full screen.
Yes. Do you see full screen? Changing slides?
Yes, perfect.
Okay, excellent. Let me just try the video. So,
yes.
You see me?
Yeah, yes,
okay.
Perfect.
Okay, perfect. Thank you.
Okay, maybe I can test next if possible.
Yelena, you please stop your. Okay.
Are my video and picture working?
Yes, John, testing the slides maybe.
Okay, yeah.
Yeah, perfect. Yeah,
Okay,
perfect. Thanks. Okay, so good morning. So I will be sharing. So good morning, everybody. I will be sharing the second part of today's session. So please, speakers, please try to keep in the allocated time, because then we will continue later on with the poster session, and we don't want to slip into that. And I will try to remind 3 minutes before the scheduled end of the talk. And so the first speaker is Jelena Jovicevic, who will tell us something about the associated Higgs production, associated with the TT bar in Atlas. So Jelena, please.
Hello, everyone. As announced, I will be presenting recent results on the Higgs boson production in association with the top quark in Atlas. The importance of this measurement relies in understanding of Higgs-top-Yukawa coupling, which is the largest coupling in the standard model, and any deviation from the standard model prediction can indicate the presence of new physics. It's relevant for the stability of the Higgs potential and the required energy scale for the new physics. So it can be directly accessible by measuring TTH production. And as most of us know, the observation of the TTH production was reported in 2018 by both Atlas and CMS with a significance of above 5 sigma. The TTH production allows also for testing of the CP structure of the Higgs-top-Yukawa coupling, indirect constraints on the Higgs self-coupling, as well as prosing the other BSM effects in the differential distributions. So the TTH signature in a detector is characterized by the decay of the Higgs boson and the TT bar pair, and the broad spectrum of analysis exploiting multiple final states are performed, and only thanks to the excellent detector performance and the hard work of all basically object performance groups, this is achieved. And generally, small branching ratios correspond to the better signal over background. So the channel studies in Atlas are characterized by the decay of the Higgs boson. So we study Higgs decay to BB bar, multi-leptons, the targets WW, tau tau, and ZZ, then gamma gamma, and also ZZ to 4-lepton decay that is excluded from the multi-lepton analysis. And of course, we perform combinations for the higher precision. So in the presentation today, I will cover all these individual channels as well as some of the combinations, and I put the links to the publication. So as you can see, the BB analysis is done using 36 inverse femtobarn data. The multi-lepton uses 80 inverse femtobarn data, while the diphoton and ZZ to 4-lepton analysis actually exploits the full run-2 data set. In the gamma-gamma channel, we also measure the CP properties of the Higgs-top-Yukawa coupling, as well as the first simplified template cross-section measurement in the bins of the Higgs transverse momentum, and this is a new result that we presented today. So starting with BB final state, it is a fully fermionic final state, and where the Higgs boson reconstruction is possible but very challenging due to combinatorics. It suffers basically from irreducible TT plus BB background that has a large theory uncertainty. And this is the biggest challenge in the analysis. For the nominal prediction, we use TT bar 10LO5 flavor scheme sample, and the relative contributions from TT at least 1V subcomponents are related to the TTBB 10LO prediction using Sherpa open loops in the 4 flavor scheme. The categorization is done based on number of leptons and the number of jets, as well as the BTAC scores of the jets, where the 4 working points are exploited. This allows for separating regions in more sensitive TTH categories, as well as the categories targeting different TT bar subcomponents. So the analysis strategy is based on the cascade of MVAs. We have first reconstruction BDT, matrix element, the likelihood discriminant that I used in the final classification BDT that in addition exploits kinematics and the B tagging information in the event and train to separate signal from the background. So the signal is extracted from the bin profile likelihood fit to all signal and control regions, and normalization of TT plus at least 1B and TT plus at least 1C background is left free floating in the fit. So we measured the signal strength of 0.84 plus minus 0.6, which corresponds to the significance of 1.4 sigma, while 1.6 sigma is expected. The normalization of TTB background is measured to be 1.24, while the normalization factor for TT plus C is measured to be a factor 1.6. The dominant systematics is coming from the modeling of the TT plus 1B background. It's actually 0.46, which obviously dominates the total background in this measurement. We also have a non-negligible component from limited Monte Carlo statistics, jet flavor tagging, jet energy scale, and resolution. And as you can see, the measurement is systematically limited and requires improvements from both theoretical and experimental communities. So the TTH multi-lepton signatures, that is very distinct multi-lepton signatures, are targeting ZZ, WW, and tau-tau decays. So first, the categorization is done based on number of prompt leptons, electrons, and muons, and number of hadronically decaying taus. You can see a schematic on the left-hand side of the slide. The main background, irreducible, is coming from TTZ, TTW, and dibosons, while the reducible backgrounds are originating from non-prompt leptons, charge misidentified electrons, and electrons from photon conversions. For the reducible backgrounds, we apply object-level discrimination, such as isolation BDT to reduce non-prompt lepton background and BDT to reduce the charge mis-ID and electron conversion candidates. Then we have a further categorization in the 2-lepton stain sun 0 tau channel. We split it into low-end jets corresponding to 2 and 3 jet beams and high-end jets that correspond to the at least 4 number of jets. So discrimination, the low-end jets actually have a discrimination power on TTW and on prompt lepton backgrounds. Their delta R between leptons, AHT, and MB jets, lepton flavor, event yield are exploited to extract the maximum information. However, in the high jet beams, the multidimensional BDT space that exploits lepton charge and lepton flavor are used, and for each TTH enriched category BDT, where TTH is trained against the backgrounds, is exploited. So the normalization of the non-prompt leptons, electrons, and muons, electrons from material conversions and from the internal conversions, as well as the TTW, are simultaneously fit in the data. You have to just know that TTW normalization is correlated between low-end jet and high-end jet in the 2-lepton say sun 0 tau, as well as 3-lepton 0 tau channels. Shapes of the backgrounds are from the Monte Carlo, taken from the Monte Carlo simulations with the extensive set of the systematics uncertainties. So just to know that in the plots shown as well as in the publication, the yellow report TTW cross-section is scaled by factor of 1.2 to account for the missing 1 jet at NLO and electro-weak corrections. So the signal is extracted from the profile likelihood fit across 17 control regions and 8 signal regions, and simultaneously the background normalization factor and signal strength are extracted. So the signal strength measured is 0.58 plus minus 0.3, that corresponds to the significance of 1.8 sigma, while expected was 3.1. So you can see also the table with measured normalization factors for the TTW background with respect to the corrected yellow report values. And you can see that all measured TTW cross-sections are constantly higher from the standard model predictions. Now moving on to the ZZ 4-lepton channel that is done within the general Higgs 4-lepton analysis. So this has extremely low rate and a clean final state with a very high signal to background ratio. So basically search for the Higgs boson candidates in a window of 115 to 130 GeV, and background is estimated from the mass sidebands. Categorization is based on the decay of the TT bar into leptonic and the hadronic categories. And in leptonic, we use event yield, while in controlling the neural network is exploited. The signal strength measure is 1.7 plus minus 1.7 statistics, and 0.2 systematic and 0.2 theoretical uncertainties. So you can see it's fully statistically dominated channel that will benefit from more data. And in total, 3 candidates in run 2 data are found. So we expect increase in precision with increasing the data set. So moving on to TTH to gamma-gamma channel, that also has a small rate, but the Higgs boson reconstructions and narrow peak can be done with a very high precision, and sidebands are also used to estimate the background. So just a reminder, the first TTH observation in TTH gamma-gamma only channel is reported in 2019 using the full run-2 data set with a significance of 4.9 sigma, while 4.2 was expected, which corresponds to the signal strength of 1.38 with around total uncertainty of 0.4. So the same data set is reanalyzed with the motivation of directly probing the CP structure of the Higgs-Yukawa coupling. So here signal yield is parameterized as a function of the kappa t and the alpha, which is CP mixing angle. So the analysis strategy is first to reconstruct the Higgs candidate as the 2 energetic photons, the top candidate using the reconstruction BDT. And the categorization is based on the TT bar decay again into leptonic and hadronic category. So this totals in 12 hadronic and 8 leptonic categories, in which 2D BDT is used in the fit. So one dimension is the background rejection BDT that using object level observable, similar as the one used in the observation. And another is CP-BDT, which is trained to separate CP even and CP odd coupling in the TTH plus TH production. So this exploits 20 kinematics, angular, and event variables. So on the left-hand side, you can see the plots corresponding to the standard model, assuming the CP even, Higgs-Topue coupling and TTH. Non-TTH TH processes are fixed, and the mu TTH is measured to be 1.7 plus minus 0.4 statistical uncertainty and 0.2 systematics, which corresponds to the significance of 5.2 sigma, while expected was 4.4 sigma. Also, the limits are set to the TH production to be less than 12 times the standard model and 95% confidence level. On the right-hand side, so the assumption was basically probing the CP structure. So the KT is also floating in the fit, and a mixing angle of greater than 43 degrees is excluded in 95% confidence level, while exclusion was expected to be at angle of 63 degrees. The pure CP odd coupling is excluded at 3.9 sigma.
Okay, 3 minutes left.
Thank you. So the latest measurement is the measurement of simplified template cross sections using the latest binning agreed within the LHC Higgs cross section working group in the TTH gamma gamma channel, and this is part of the global Higgs to gamma gamma simplified template cross section measurement that is released for the ICHEP now. So the TTH cross sections are measured in the bins of Higgs PT. So the bin boundaries are at 60 GeV, 120, and 200 GeV. So the strategy is the diphoton events are classified using multi-class BDT trained to separate different STSX bin, and each class binary BDT is used to separate signal and background. So here you can see the example of the bin between 60 and 120 GeV. So you can see the multi-class BDT output on the left-hand side and the BDT score on the right-hand side. And here you can see the results of the cross-section normalized to the standard model prediction on the top and the total cross-section in the table on the bottom. And you can see that all measured cross-sections are compatible with the standard model in each PT bin. So this brings me to the summary. Atlas has established the observation of the TTH production. The result is compatible with the standard model prediction. So here you can see an extract of the plot from the latest Higgs combination. So where we combine 36 femtopanel BB and multi-lepton channels with 139 femtopanel from gamma-gamma and ZZ2-4 lepton channels. And yeah, so you can see that measurements are compatible with the standard model. And Higgs-top Yukawa coupling CP structures is also studied in the TTH Higgs to gamma-gamma channel, and CP mixing angle alpha greater than 43 is excluded at 95% confidence level. The TTH production is for the first time characterized through the measurement of the simplified temporal cross-section in the beams of Higgs transverse momentum, and the result is again compatible with the standard model prediction. So the challenging backgrounds for the TTH-BB and the TTH multi-lepton measurements, which is TTBB production and TTW production, require improvements from the both theory and experimental communities. And please stay tuned for the full run tour results. Thank you.
Okay, thank you, Jelena. I'm sure there will be some questions. Please, raise your hand. Okay, Julie, go ahead.
Yes, I know this question was already asked this morning, but I didn't have the mu in mind. So the mu for TTH gamma-gamma in the CP analysis was 1.7 plus or minus 0.4, something like this. And now it's 0.90. In the STXS analysis, it's 0.92.
Yes, in the STSX analysis, let me just find, I didn't report it, I think, sorry. I think
so
it's...
I have a... So
this is
did you do a compatibility test? Because you said this morning it was 1 sigma, but it looks like it's more, no?
Well, as far as it has been checked, and it's a 1 sigma compatible between the one
because
report.
This is the same data set, right? So, I mean, the difference is quite big. Huh? And do you know where those events are gone? And if, I mean, in which categories they are gone? And maybe it's due also to the fact that you float other production modes, signal strengths.
Exactly. This is done simultaneously in the global Higgs to gamma fit, while in the CP paper, this is done only using TTH events with the other Higgs production modes here fixed to the standard model predictions.
So those events who left the TTH categories, you know where they've been? Or maybe not.
I'm not sure exactly about all the details. I just know that first of all, the fit is different. This targets the global Higgs to gamma-gamma. The categorization of the events is different also in terms of which events are used and how they are split. And unfortunately, I don't know much of the other details, but maybe someone, if someone from Higgs to gamma-gamma also connected can comment.
Okay, well.
Okay, thank you.
So anyone else wants to raise a question? So doesn't seem to be the case. So thank you, Jelena, and we can move to the next talk by Carlos on the electroweak boson scattering.
Oops, sorry for that.
Carlos, please.
Hello.
Yes, we can hear you. Please share your slides and video eventually.
Yep. A second. Can you see my screen?
Yeah, I can see the agenda.
Oh, sorry. Back to... And now it should be...
Yes.
Okay.
Make it full screen. Okay, perfect. Go ahead.
Perfect. Okay. Good morning to everyone. I'm going to be presenting this work called subquark loop corrections to WW scattering in the context of the electroweak Lagrangian. And this work has been carried out with Antonio Dobado and Juan José Sancillero from Universidad Complutense de Madrid, and also members of IPARCOS Institute. I'm going to introduce real quick what is our objective here. So since the discovery of the Higgs boson in 2012, much work has been done in understanding how the Higgs couples to gauge bosons and quarks. And we know there's a margin for some deviations. And the hypothesis of our group is that these deviations may come from a strongly interacting new physics sector, where the Higgs boson and the Goldstone bosons could be composite states of and members of some other a multiplet maybe of some other symmetry, a higher symmetry group. And in this work, we want to compare the loops that may induce new signals for new physics in LHC, and compare in particular the loops arising from fermion corrections with the ones arising from loop corrections, from boson loop corrections, because most of the times the fermion loop corrections are neglected. And we want to see if this approximation holds, or there's a range of energy where they can, there could be an interplay between those two corrections. So we know that these corrections, the boson corrections dominate when we go to higher and higher energies, for example, like 3/10 or below 3/10. But we want to focus in this work in just the imaginary part of the fermion corrections. Why? Because they enter in the expansion in actual leading order in our effective field theory. So they are not masked by the leading order corrections that are only real. So, and because we're working in the effective field theory, we have freedom for the couplings of our model. And we want to know if there are values for these couplings that may induce a higher correction arising from fermions. So I'm going to introduce the Lagrangian. This is based on this spontaneous symmetry breaking pattern. We have the gauge bosons, which transform nonlinearly under this symmetry, and the Higgs that transforms linearly. We can order this Lagrangian in powers of chiral dimension, where the first term would be L2, the second one corresponding to chiral dimension 2, and the next one L4 of chiral dimension 4, and so on. And when calculating scattering amplitudes, it's often used the equivalence theorem, where we can relate the longitudinal components of the W bosons to the Goldstone bosons of the effective field theory. And this is a correction up to this order, the mass of W over the square root of the center of mass energy. So our Lagrangian is this one, where we have the Higgs and coupled to the bosons in the CU matrices, and also the Higgs coupled to the quarks. And this work is going to be focused only in the top quark, because the corrections of the fermion loops are proportional to powers of the mass of the fermion, and we want to estimate how strong these corrections are. So we will only take into account the T-top, the top. And so these functions right here correspond to this expansion in powers of the Higgs. And we want to pay attention to the couplings A and B and C1, because these are the ones that are going to matter in the end. So we can recover this in the model if we set A and B to 1 and C1 to A. Yeah. So like I said, we want to know how important are the loop contributions. And what we have done is calculate the contribution of the quark using the Unitarian functional. We have obtained the scattering amplitudes. We have renormalized the couplings, and we have compared them to some works that have been done recently, and we have found an agreement. And we're going to compare the amplitudes and take into account just the partial wave amplitudes for this case, for the W plus, W minus going to W plus, W minus. And so we're interested in this ratio, which is the imaginary part of the, well, we have both. We have the real part and the imaginary part. But like I said, we're going to focus more on the imaginary part. And we're interested in this ratio of the imaginary part of the boson loop contributions and the fermion contributions. In this part, in this term right here, we have intermediate states coming from W plus and W minus, CC, and HH. And it's important to note here that the CC and NH in this calculation enter using the equivalence theory, and also in the fermion, also for the fermion contribution, while the W minus and W plus enter in the exact way. So we're going to analyze the results for these partial waves, at least for the first two. And we have here the ratio that I just introduced. And if we vary the parameter A, setting B and C1 to 1, we can see that there are corrections of order 30% and around 500 GeV, and above 1 TeV, the boson contributions dominate. Also, if we do the same thing for B, we find a similar plot. But the most interesting parameter is the C1, because if we keep A and B close to 1 and we just change C1, we can see that there's a larger region where we can find contributions of 80%, and even for values close to 1, we can have like 60% correction. So we have scanned all the ratios that for this region of parameters A, B, and C1 from 0.9 and 1.10, which are the usual values that, well, more than we have extended the region of the experimental values for A, B, and C1. And yes, and well, actually B would go from minus 1 to 2, but we have kept this limit. So we can see that the lowest ratio for the partial wave, for the first partial wave, A0, would come from the free TEF, would come from just setting A and B to 1 and setting C1 to 0.9. And the values also over 1, but close to, like you can see the plot here, but close to 1 actually don't yield a low ratio, which would mean that the fermion contributions are important. We have to go to values like 1.1 to see an effect coming from fermion corrections. And we can do the same thing for the next partial wave, A1. In this case, because of the symmetry, because of the way the expression of the amplitude and the way we're projecting onto the second partial wave, the amplitude does not depend on B or C1, it just depends on A. And this plot is even more dramatic because we can see that for values, even at high energies, we can have a higher correction from fermion loops. And it's important also to notice that because of what I just said, that some terms of the amplitudes vanish because of the parity of the wave, the contribution arising from fermions is the same as the one we have in the standard model, because the bosons just depend on the parameter A and B, and the fermions depend on C1. So in the end, because of the parity of the amplitude, we just have a dependence on A. Here I have plotted the ratio for the first partial wave for a fixed energy, like 1.5 TeV and 3 TeV, and we can see that, like I said, we can move from a range of even like a 99% correction up to an 80% correction for values close to 1.2. Yes, and yes, for example, for the 1.5 TeV, we can see that the best value we have found is A equal to 1.6, while for TTV, the best value is 1.002. And we have done also this, but for a specific scenario, which is the minimal composite Higgs model. And where we have chosen a scale of energy where the Higgs could present itself as a composite state, and from this would be this F. So from this we can calculate the actual value of the A, B, and C1 parameters. So we have plotted this, and we can see that for the first partial wave R0, we can find a corrections of 40 to 9%, even for low energy. And we can see that also for next partial wave R1, this corrections is even more dramatic in the beginning. And this is actually something that we were not expecting. We were not expecting that even for values of the standard model of the couplings close to the standard model, there will be such a high correction for this channel. And this brings me to my conclusions. So we have estimated the fermion corrections to the W scattering and compare them to the bosons ones, and we have found that in the most of the parameter space they're negligible, and that there are some parameters where actually the fermion contributions may dominate or may be of the same order of the bosons. And for instance, we're given some values here for the A0. We can find out from a 70 to 85 correction for these values of A and B equal to 1, and C1 close to 0.9 in this region of energies. And for the next one, we can even find a bigger correction for the partial wave A1, and for values close to 1.2. And like I said, it would be important to check other models, like the minimum composite Higgs model or the dilaton models that we're working on. And like I mentioned 5 slides earlier, it's important to control the contributions arising from HH and CC intermediate states when we're working beyond the equivalence theorem. But in this case, they don't. They just play a role in the first partial wave, not in the second one, because they're not of the equivalence theorem. And this is all. Thank you for your attention.
Okay, thanks a lot. So questions, please. So I don't see any. So maybe I can ask. So, well, if you go to your summary slide, please.
Yep.
So regarding the WW scattering, so you examine the corrections for the high energies between 1.5 and 3 TeV, right? So I think that means that we can only expect some deviations to be seen only at the future colliders, right? Not at high lung LHC yet.
Yes, actually, it would be for this channel. We can see that, like mentioned in the this plot right here. If we go to not so high energies, there's still like a high correction, further 30%, 70% for this wave. For the A01, I think it's not that much. But for this one, yes, we can see an important correction.
Okay, thank you. So, any other question to Carlos? So, if not, then thanks a lot again, and we can move to the next speaker, Ms. Menk, about the JHU generator.
Okay. Let me share my screen.
Okay, you can see this size.
All right.
Okay.
Okay, thanks. So I will start.
Okay, go ahead.
This talk is mainly to introduce the J2 generator, some new features that we recently developed for the Higgs boson studies, and the work is based is done together with the authors listed here, and you can find the details of the work in the two papers I put here. So first, a brief introduction of the J2 generator and the Mela package. So J2Gen is an event generator that basically we are focusing on anomalous couplings of the Higgs boson and also the corresponding EFT coefficients. Together with the generator, we also provide the matrix elements that's either calculated from the generator that we call J2J Mela, or the calculated in an analytical way, which we call analytical Mela. These matrix elements would help us to build discriminants that can use to optimize the analysis and suppress background. Also, analyzers can use a matrix element to do per-event-based reweighting so that they can switch from one model to another. And recently, we also have developed J2Gen lexicon. This is a package that we use to do some conversion between different EFT bases and also the anomalous couplings, so that they can the parameters can be translated from one to another. So I also put the web page here and a snapshot of the generator here. Briefly about what's available in this generator. Yes.
Can you hear? You need to change slides somehow. They're stuck.
Okay, I'm changing, but if you cannot see
No,
it.
we only see the first slides so far.
Okay, sorry. I don't know what's going on.
Yes, now it moved. Yeah.
Now you can
we are
see
on slide 3. Yeah.
Okay. I don't know if it's because of full screen. So I'm on slide 3. Maybe I would just put it like this. And can you see the slide right now on slide 3?
Yes, go ahead.
Okay. And if I change slides, can you see it?
No, it stays on slide 3.
Okay. All right, then I will quit full screen. So I'm on slide 3. Sorry about this. So what's available in this generator and the matrix element? So we provide basically all the production modes for the Higgs boson at the LHC, basically. The left are the production mode that we include. So through these production mode, we can probe the anomalous couplings of the Higgs boson with either vector bosons or fermions. Some of the processes include both. For example, the Wu to ZH, there will be contributions from both fermion and vector boson vertices, and also the THQ, for example. And I will go through some of the new features later, but just briefly, about all these production modes, the users can configure whatever anomalous couplings they want to have in the final events through some very easy configuration. Apart from the generation of the Higgs boson, through J2Gen, it also talks to other generators. So if the Higgs boson is produced through other generators, the J2Gen can also do the decay to different final state, and the supported final state are also listed here. The main final states include vector boson final state to 4 fermion final state, or 2 fermion plus gamma or gamma gamma. We also support tau tau, and there are also other final state the J2Gen can be interfaced to Pythia. So in addition to the spin 0 Higgs boson, it also supports spin 1 and spin 2 models, which we put as Z prime and G here. And it also supports a heavier Higgs boson, for example, if the mass is larger than 125 GeV, and if it's non-standard model, like the generator also can support it. In addition, it also has the off-shell production for the gluon fusion and electroweak processes, and for the fermion dominated initial state, we only support on-shell production. And there are some processes we also support NLO, like the TDH and QQ to ZH. So this is just an overview of the generator and the matrix element. So the announced couplings that supported by the generator and matrix element can be basically described in these two formulas. For the couplings to vector bosons, we can generally write the scattering amplitude according to the vector boson's tensor structure, and there are three major tensor structures. And the coupling constants in front of them basically are the anomalous couplings that one is interested in. And of course, there's also the standard model one here. For the fermion couplings, we also write have two structures, the CP even and the CP odd one. The CP even is the standard model one. So basically, for standard model at tree level, only the one in the black circle has non-zero value, and everything else has zero value at tree level. And the circle in orange are from the CP odd, and the others are from CP even states. And these anomalous couplings can be translated one-to-one to effective Lagrangian terms. For example, if we express write the Lagrangian in Higgs spaces, then these G to G4 couplings can have a one-to-one correspondence to the EFT coefficient in the Higgs spaces Lagrangian. Of course, it can also talk to other EFT bases like Wasserl bases. So all these conversion can be done through J2J lexicon. And as I mentioned, there are also matrix elements calculated from the generator, and these matrix elements can be used to improve the analysis. For example, to build discriminant. There are two concepts to build a discriminant. One is to separate one model to another. So you calculate the probability of the for the event according to one model or to another, and you build a discriminant through these probabilities to separate the two. And here I give an example of the VBF events where we're interested in the Higgs vector boson anomalous couplings, and you see that if it's standard model or if it's CP odd coupling, then this discriminant can really separate the two very well. And also there's another discriminant that can be built from the matrix element to get the interference between two models. And again, here give the example of the interference between CP odd and CP even. And this discriminant can have a forward-backwards asymmetry when there is equal mixing between CP even and odd state, but with different signs, they have different patterns of asymmetries. So these kind of a discriminant can be used to optimize the analysis. Of course, partial kinematics also carry very useful information, still using VBF events as an example. For example, the delta phi between the two jets could also carry the information that they look very different. But when you quantify that, for example, through the ROC curve, how the CP even and odd event can be separated through these observables, you can see that the delta phi JJ is much worse than doing a matrix element-based discriminant. Of course, some other techniques cannot be also used to build such discriminant, for example, the machine learning techniques. And using BDT, for example, to combine all the inputs that are the same used to build the matrix element discriminant, one can achieve more or less the same performance as you can see here. But when it comes to the interference, then the machine learning is a little bit need a little bit more work to separate the interference with different signs, as you can see here. So In the recent work, we give some example of how we can use these matrix element discriminant to build an analysis that can constrain all the, for example, Higgs VV announced couplings all at the same time. And we showed the example in the Higgs 2,4 lepton final state. And the red curve here shows the log likelihood of, for example, the fractional cross-section of the CPR, the announced coupling. And this one shows the higher order CPR, the announced coupling. Compared to that, if we use, for example, the simplified template cross-section beams as discriminants, that is basically equivalent to using, say, Higgs PT or the invariant mass of the two jets as discriminant to do the analysis, then you can see the log likelihood in blue, and you can see that the performance is a little bit worse than using the matrix element discriminants. Also, in simplified template cross-section, because the Higgs decay information is not fully explored, you can see in this region where basically we gain from using the Higgs decay information, there's a big difference. One also show here, if we just use Higgs 2,4 lepton decay, but not the production modes, what the likelihood would look like, and this is showing in the green. And you can see that in the central region, this region is basically dominated by the production information, but because they have higher Q-squared and there might be dependency on Q-squared, so using decay-only information is more model independent. And these are the examples that we show here. And if we try to constrain the announced couplings of Higgs VV all at the same time, which we listed here, the 4 announced couplings we're trying to measure here. And these can be translated to EFT coefficient in the Higgs spaces, as we listed here. And one can just constrain these EFT coefficient all at the same time. And here, these plots are just showing the 2-dimensional projection of the likelihood. And you can see all the patterns here. Of course, we only do this in the Higgs 2,4 lepton final state as an example. So other couplings are not really, we don't have really the information of other couplings. So there are some assumptions made. For example, the Higgs BB coupling is fixed to standard model, but the gluon fusion coupling is floated as a free parameter in these results. Just to clarify what assumptions we made when we made these results.
3 minutes left.
Okay, these are just the examples, and there are new features that we recently added to J2Jane. For example, for gluon fusion, we start to look at the vertex either through top loop or bottom loop, or when it's point, like what it look like. And you can see from this plot, first of all, if you look at the on-shell Higgs, when it's produced through 2 jets, we can look at the correlation of the 2 jet and the Higgs, and we can probe the effective Higgs glue coupling. Or we can interpret this loop as top or B quark coupling. But through the on-shell, we cannot really tell the difference of top or B loop. We can only assume that the couplings are the same. So here we just show what we can constrain on these kappa F and kappa F tilde. But if we go to off-shell, then through looking at the Higgs off-shell tail, we can see the difference of the top loop, bottom loop, and when it's a heavy point-like interaction, you can see that the off-shell shapes can be very different. So through off-shell, we can tell what's happening in the loop. This is just one example. What we also added is the ZH final state. So first of all, we include an NLO effect in the QQZH process as shown here. So this is the diagram of QQZH, and this is just one example of NLO. And one can see that the next leading order correction for the announced couplings are basically flat through all the regions for QQ to ZH. We also look at the GLU to ZH if we can use it to constrain the announced couplings. For GLU ZH, we have the triangle diagram and the box diagram, which you can see one is dominated by the Higgs ZZ coupling and the other through Higgs TT coupling. So these two diagrams, as you can see from the ZH distribution, the triangle is a blue one and the box is a red one. So they're sizable, but they also have destructive interference. And in the end, this is a magenta of the blue ZH. So we studied that if we have enormous Higgs VV couplings, then the triangle cross-section will go to 0. And for the box diagram, if we have enormous Higgs TT coupling, then you can see the MZH would have very different behavior. So we can use the blue ZH to constrain the Higgs TT enormous couplings. The other feature that we add is the off-shell production of the gluon fusion and electroweak processes. And in these processes, we consider the Higgs enormous couplings and how it interferes with a background, which we use an MCFM matrix element to calculate. Also, we allow additional Higgs boson with heavier mass. So the three terms would interfere with each other, and it's characterized in our generator. And here we show the example. So here, these diagrams shows the gluon fusion signal and background, and the electroweak signal and background, and the two are the signal and background are interfering with each other. So under EFT relations, enormous Higgs VV couplings would also yield enormous gauge self couplings, and this would mean not only the Higgs shape tail would change in the off shell, but also the background can change when we have enormous Higgs VV couplings that's shown the dashed black and red. This is how the background would change, and the solid black and magenta line shows the overall signal background interference, how would it change. So you see the background also contribute half of the change in the overall shape. The other feature, as I mentioned, is that we add additional resonances with an arbitrary mass and width that also allows enormous couplings. Here we show the example of the gluon fusion production, where the additional Higgs boson with 450 GeV are shown here, how it interferes with the standard model Higgs and the background. We also consider, for example, if the gluon fusion loop is not dominated by top and bottom, but it's point-like, and how the shape will look different. So these are the new features that we add in the generator. The generator and the matrix element are widely used in the experiments. Here I just show several results from CMS. This is the TDH gamma-gamma enormous coupling measurement, and these are in the 4-lepton final state using on-shell and off-shell Higgs production. And there will be more results from CMS, and you can see the details from the talk of Savas, just 2 talks after. So just to summarize, here we present a general framework to study the enormous couplings of the Higgs boson. And these tools are very useful to, to measure the enormous couplings and the corresponding EFT coefficients. And there has been new features that we developed recently. We give examples of how we can measure the multiple Higgs VV EFT coefficients at the same time. We have included the gluon fusion and electroweak on-shell and off-shell enormous couplings in the generator. We give an LOZH description and also include additional resonance with enormous couplings. So in the end, if you here I just put more information in the slides. So if you have more to discuss with me, I also have a Zoom room here after the session closes at 1 o'clock. If you want to discuss more, you're welcome to join. That's
okay,
it.
Thank you. So questions, please. So I don't see any hand raised. So, well, I think it's, oh, Tanya, please.
Yeah. Sorry, I have a question. Can you hear me?
Yeah.
Yeah, fantastic. Do you know anything? I mean, using this matrix element method, can you comment on runtimes with respect to other methods to measure these anomalous couplings, for example? Is there disadvantage or advantage or?
The runtime, you mean how long does it take to get the matrix element?
Yeah, I mean, if I understand it correctly, you really compare generated matrix elements, so to say, instead of what people usually do, shape discrimination and so on. So you have to regenerate this in a sense, right? To map it.
So all you need to do is pass the full kinematic information of your final state particles, and you pass it to an interface, and it will calculate the matrix or the probability for you. And it's if it's just one probability, it's rather quick. It's maybe just a few seconds to get it. So it's not like machine learning that you really need to give a lot of sample and events to train. It's just one calculation per event base.
Okay. So it's not an issue. This is the short answer, I guess.
Right.
Yeah, okay, thanks.
Okay, thank you. Anyone else wants to raise a question? Well, if not, so then, as it was mentioned, so there's a specific Zoom room open for the further discussion, or eventually you can post your question on the MetaMouse. So thanks a lot again, and let's move to Adinda, who will be summarizing the CMS Higgs combination.
Hi, can you hear me?
Yep.
Okay, let me just share my screen and make the slides full screen.
Yeah, perfect.
I think you can also see the video still in the screen, right? So I should.
Yeah.
Yeah, no, but yeah, okay, I'll put that in the corner so that you don't have to look at my face twice. Okay, so let me start. I'm going to be talking about, as you said already, about the Higgs boson combination results from CMS. And of course, this doesn't need a very big introduction. Higgs physics in run 2 of the LHC, we've already seen lots of nice results today. In this session, and also already some yesterday. But nevertheless, I wanted to just remind you what the focus has been for Higgs physics in run 2 of the LHC, which has been to do very precise measurements and to go beyond inclusive measurements, so to try and measure things in a more finer grained way. And as you can see from the two summary figures I put on the slide here from CMS Higgs to gamma gamma and Higgs to tau results, which also already have been presented today, you have these nice measurements in the simplified template cross-section framework, and this is how we're going beyond the inclusive measurements. And of course, you have all this nice information from all the individual production and decay modes, but ultimately the best precision comes from doing combined measurements. And for this reason, I'm going to be talking to you today about combined measurements that were done in CMS. So first, I'll briefly summarize the combined mass measurement, which you've already heard about earlier today in the ZZ and gamma gamma talks. And then I'll talk about the coupling combination and also an EFT interpretation based on the simplified template cross-section measurements. So briefly on the Higgs boson mass measurement, of course, this is not done in all Higgs boson decay channels. And in our case, we do this measurement in the Higgs to gamma gamma and the Higgs to Z to 4 lepton channels. And the measurement was performed using data collected in 2016 and also combined with data collected during run 1. The Higgs to ZZ result was already made public several years ago, and you can see the mass spectrum here on the right from this analysis. And the best fit Higgs boson mass was 125.26 GeV with a statistical uncertainty of 0.2 GeV and a systematic uncertainty less than 0.1 GeV. The Higgs to gamma gamma mass measurement is more recent and relies on very precise photon energy scale calibration. So this obviously takes a little bit more time. And you can see the mass spectrum again from that analysis here on the left. And the fitted mass was 125.78 GeV with statistical and systematic uncertainties both of 0.18 GeV. Now in combining these results, of course, we can get better precision and we can do many sub-combinations. So I'll show the likelihood scan of one of those sub-combinations here on the left, where you see just the combination of the 2016 data. So in red, you see the scans for the Higgs to ZZ result, in blue for Higgs to gamma gamma, and in the middle, in black, the combination. So these two masses, of course, are slightly different, and you see the combination lying nicely in the middle. And this is also visualized here on the right. So all these curves that you see on the left correspond to this green block here on the right. Now putting the 2016 Higgs to gamma gamma and Higgs to ZZ results together with the data collected in run 1, we find this best fit mass here, which I've highlighted in blue, and we get a best fit value of 125.38 GeV with an uncertainty of 0.14 GeV, and this is mostly statistics. And you see that the precision there relative is 0.11%, which is really very precise, especially if you compare with previously most sensitive measurements, which had a precision of around 0.2%. Moving on then to the coupling combination. Of course, in the coupling combination, we're actually introducing a lot more different production and decay channels, and we try and target all the main channels that we have available. And on the table here on the bottom, you can see which main production and decay channels have a targeted analysis included in the combination. So as you can see, there are a few gaps. So we have in this combination that we've performed, there are a few targeting channels that weren't yet included, but we hope that for the full run-through combination, we can close all those gaps. And for the remainder, I'm also showing you in the table which data set was used or which size data set was used. So as you see, for the Higgs ZZ channels, we have already the full run-through data set included, 137 inverse femtobarn. For many of the other channels, we had the 2016 and 2017 data sets available with around 77 inverse femtobarn. And for a few of the channels, we only had 36 inverse femtobarn available. But also a lot of those are being updated or have already been updated. But of course, doing combinations takes a little bit of time. So we don't have those very latest results included in a combined measurement yet. Now, there are many results that we can get from combining all these different analyses, and one of them is signal strength measurement. So here we just define a model where we have signal strength modifiers, which we label mu, which just scale the cross sections and branching ratios relative to the standard model. And you can do this just for the production side. So this is what you have here. So just the cross section relative to the standard model. You can also do it just for the decay side, or you can do a very littly constrained model where you have a separate signal strength modifier for each production and decay combination. And you can also go the other way and define a signal strength modifier for all production processes and decay modes together. And we also looked at this model. And when you do this, we find a best fit overall signal strength of 1.02 with an uncertainty of around 0.07 and theoretical, experimental, and statistical uncertainties contribute in roughly equal amounts. And compared with the 2016 only CMS combination, we have a relative precision improvement of around 25%, and this comes from all of these different sources across the board. So we've got more data, we've improved some of the uncertainties as well. Going now to our least constrained signal strength modifier model, to show you the summary of the signal strengths per production and decay mode. So this is quite a busy plot, so I wanted to point out all the things you can see. So on the x-axis, you have all the different production modes. On the y-axis here, you have the different decay modes. And we've put a dashed line for the standard model expectation, which is of course 1. In the blue line with the blue band, you see the signal strength modifier per production mode combined, including its 1 sigma interval. And all the individual points here just correspond to the signal strength per production and decay mode combination. And as you can see, also from the p-value that we've reported here at the top, we have very good agreement with the standard model expectation. And if you look at the sizes of some of these uncertainties, especially in this region here, but also down here, we already have quite precise measurements in some of these production times decay channels. And if you look at this corner here in the bottom, of course, here we still have very large uncertainties, and with more data, we can still make big improvements there. Another way to look at these combinations is to look at the coupling modifiers or kappa model, which is just a parameterization of inclusive production and decay rates. So for a particle that enters in a production vertex, we have a kappa squared equal to the cross section relative to the standard model expectation, and where this particle enters in the decay vertex, kappa squared equals the partial width into that decay relative to the standard model expectation. And now there are different ways in which you can actually make this parameterization. So you can either look at effective vertices, or you can resolve the loops in the production and decay mode. So I've put an example here for gluon fusion production. If you resolve the loops, then you're really looking at the vertex here, and you're parameterizing this in terms of, for example, kappa B and kappa top. Or if you do the effective vertices, you don't care about any of the particles that appear in the loop. You just introduce one kappa gluon which governs this production vertex, and that is the model that we were looking at here on the right, where you see the effective coupling modifiers with this partial run-to dataset combination. For your benefit, I've also included here alongside the precision of most of these measurements. So as you can see, we already measure most of these couplings to a precision of 10 to 20%. The only exception here where the coupling or the uncertainty is still very large in this combination is kappa mu, where we have around 90% uncertainty. But I want to remind you that this in this combination, we only had the 2016 Higgs to mu mu analysis available. So that only used 36 inverse femtobarn, and this analysis what drives the uncertainty on kappa mu. And if you were listening to the Higgs session yesterday, or maybe in the replay, you might have seen the recent Higgs to mu mu result from CMS, which also included a new coupling modifier scan combined with other Higgs boson channels. And here we find with that new full run 2 data set that the precision is also at around 20% if you look here at the uncertainty on kappa mu from this new analysis. So we're also getting into the precision realm for that parameter. Okay, so now I wanted to change tracks. So far, we've only been talking about inclusive measurements. And of course, this is very nice, but we haven't really discovered any direct new physics at the LHC so far. But that doesn't mean that there isn't direct new physics. The point is just that it might be hiding in tails of some of our distributions. So I've drawn this diagram here. So let's say I'm doing an inclusive measurement of some quantity, some production mode. But in that production, there is some new physics which changes the tail of the Higgs-BT spectrum. I'm doing an inclusive measurement. I'm mostly probing this region here, right? So because that's where most of the events are. So I might not find any deviations from the standard model, or at least not significant deviations. And I'm missing this new physics contribution, which would be very apparent in the Higgs-BT tail. So another way to try and target these kind of deviations is to use more granular information. So you divide up the Higgs-BT spectrum maybe, and you try and do a measurement in each of these bins. And now you might be able to see that there is a deviation in this region. Now, if you have a deviation there, you might wonder, okay, what does this mean? What new physics is actually responsible for that? And so a coherent way to do that is to consider such measurements in the effective field theory framework. So what you do is extend the standard model Lagrangian by an extra term with higher order operators, which are these O's here. And now the interpretation I present here, we're using the more granular information in the form of the SDXS categorization. The reason that I didn't present a combined SDXS measurement is that in the analyses that we've included in this combination, we had a mix of different simplified temper cross-section stages because the analyses were done at different times when that framework was in different stages of development. Of course, this is only one way in which you can approach this. It's not necessarily the most sensitive and has some other limitations, but you can see other approaches done in CMS with more directly targeting these different EFT couplings in the talk by Savas, which is directly after mine. So you can just stay in the session. Nevertheless, I wanted to tell you what we did with the combined SDXS EFT interpretation. So the way to approach this is for each SDXS bin, we have to know what the cross section would be under a given EFT set of EFT parameters, and you can parameterize this by having you have the standard model cross section plus an interference in the BSM part, and in the end you want to calculate a scaling term for each SDXS bin to see how the cross section would vary under different EFT phase space couplings. So you have you can divide through by this standard model cross section, and that gives you a formula like this. So these CJs are just the EFT coefficients, and they're proportional to the F over lambda that we saw in Lagrangian on the previous slide. And we need to calculate these values of A and B, which we can do. I've purposefully not on the right already shown you the result, but I wanted to show you the coefficients, and it might not necessarily mean too much to you what all these coefficients are. But just for these two, for example, you have CHW and CWW minus CB. These are coefficients correspond to operators that affect vertices with Higgs bosons and vector bosons. And you can see, for example, if you now just look at ZH production, so just this diagram here, if you look in the different SDXS bins, you can see the different scaling functions. This is just the linear part. And so you see that we have different constants in front of our EFT coefficients. And this is how we then generate, this is then how we get the sensitivity to these different operators.
2 minutes left.
Okay, thanks. So now I can finally show you the results. So as you've already seen in terms of the coefficients that we had on the y-axis here, we only consider 7 coefficients. We're using here the Higgs effective Lagrangian model. So there are different other EFTs that you could use, but we haven't done that yet. Of course, this is a work in progress. And we only consider here the 7 coefficients that affect the Higgs sector of this Higgs effective Lagrangian, and the CP violating operators are ignored. And you can see our results, our resulting best fit values for each of these operators. Here on the right, we have a version where we float all the parameters together at the same time. That's the black points and the black lines. And we also look at each of these coefficients in turn, and that's the blue points with the pink bands. Overall, we see we have very good agreement with the standard model expectation, and on some of these coefficients, we can already see we have quite stringent constraints. But of course, there are some caveats with this method, as I said before as well. Okay, so now we come to the summary. So I've presented results on the combined measurements of the Higgs boson properties from CMS, presented the Higgs boson mass combination, where we have a precision of 0.11%. And I've also shown you our signal strength measurements and coupling modifiers and an interpretation of the simplified template cross-section measurements in the EFT framework. So far, everything is in agreement with the standard model expectation. And we already have very precise measurements available in some channels. But of course, we expect to get even more precise results from full run-2 combination and also later combination with Atlas. So stay tuned for that. Thanks.
Okay, thank you. So questions to Adinda, please. I don't see any. So, okay, maybe can you just remind us what kind of measurements can distinguish between the sign of the kappa Z and kappa W?
So this is, for example, from TH production, which actually at the moment isn't included as a direct targeting analysis in the combination. But for example, in Sergio's talk, you already saw, so, or it was kappa W and kappa T, but a relative sign, but you see that there actually kappa W is in the positive region for the best fit. But that was from a TH dedicated analysis, which of course we don't have in this combination.
Okay, okay, thanks. So any question more? Well, if not, then thanks a lot again, and let's move to the next talk. So by Savas.
Hello, I hope you can hear me and I hope you can see my slides well.
Yes, just make it maybe full screen.
I hope,
yeah,
yes, okay.
Perfect.
Okay, thank you. I guess I will be starting. So hello everyone, my name is Savas and today I will be presenting measurements of the anomalous Higgs couplings performed at CMS. Basically, there is a long history of results since the run 1 of the LHC from CMS, measuring these couplings of the Higgs. And this is important because, first of all, we need to fully characterize all the properties of the Higgs that we discovered in 2012. These precision measurements are an excellent probe of new physics. And also we need to see if there is considerable CP violation hiding in the Higgs sector. The presentation today will be focusing on results mainly from the case of the Higgs 2,4 lepton and dedicated measurements of the anomalous couplings. As you can see at the bottom of the slide, there is a list of related talks to these results. So one can parameterize the Higgs couplings using the mass eigenstate basis with these two expressions that you see here for the fermion couplings and the vector boson couplings. What is interesting here is that you can see the standard model contribution, for example, with this A1 coupling, and then you have the A2 and A3 couplings, each one being a CP even and CP odd contribution to this scattering amplitude. This scattering amplitude is related to a fundamental Lagrangian density, which you can see written out below for VV at least. And through this, we can relate the anomalous couplings to actually Lagrangian coefficients, and then one can do, for example, an interpretation. So in the results that I'm going to be showing today, we have adopted two different approaches with respect to the relations between the anomalous couplings that we consider. In the first approach, the custodial symmetry is considered, and also all the WW and ZZ couplings are considered identical. In the green circles, you can see the 5 independent couplings that at the end of the day we scan. And in the second approach, what we have done is that we have considered the SU2 cross SU1 symmetry, and thus we have enforced the EFT relations between the anomalous couplings. And the result of them is to reduce the number of independent HVV couplings to 4, which you can see again here with the green circles. And this is what we will be considering in the results today. The amplitude that I have described in the beginning is actually the most general Lorentz invariant form for for operators up to dimension 6 that you can write out. It's possible actually to perform rotations from the mass eigenstate basis that these amplitudes were written in to any other, for example, the Warsaw basis. But why am I saying this? I'm saying this because this most general form that these amplitudes are written tell us that actually we need to perform an optimal analysis that really is dedicated to measure this tensor structure of the anomalous couplings and also correct. And how do we do that? So first of all, we use dedicated discriminants that try to exploit all the available kinematic information in order to boost sensitivity to these anomalous effects. And these are based on matrix element methods. And also, we fully simulate all the anomalous effects through the detector. So there are two types of results that are going to be reported today. The first type is actually the fundamental measurement that we do, which is the measurement of the fractional anomalous coupling contribution in the signal strength, which you can see with this form over here, this ratio of couplings and cross-sections. We do this because this has some very good characteristics. First of all, the total width of the Higgs is absorbed in this ratio. The second thing is that uncertainties that, and systematic uncertainties that otherwise you will need to consider are actually cancelled in the ratio. And this is a very well-bounded quantity in between -1 and 1. Of course, one can go then and perform an interpretation in terms of the Lagrangian coefficient. But here, there are some assumptions that need to be made. First of all, the total width of the Higgs come into play. And then because of this and the fact that the anomalous couplings are actually modifying the total width of the Higgs, one needs to implement how these anomalous couplings are modifying the total width of the Higgs, and also assume that no other phenomena are affecting the total width of the Higgs. Once this is done, an interpretation in terms of the direct couplings can be performed. So going back to the experimental part of this talk, actually, so we select Higgs decaying to 4 leptons, and this is done with the Higgs decaying to electrons and muons. And then what we do is that we create categories in which we try to enrich specific production modes. So we have categories, a VMBF tagged category and a VH tagged category. And in order to create these categories, we use matrix element-based discriminants that try to separate these production mechanisms against, for example, gluon fusion, but also against our background. Furthermore, dedicated discriminants try to ensure that we have an optimal selection of also the anomalous couplings events by having these dedicated discriminants that target specifically anomalous hypotheses. And then once we have this collection of events, we perform template likelihood fits on, again, matrix element-based discriminants. There are two versions, general forms of these matrix element-based discriminants that we use. There is the alternative version, which basically tries to distinguish between two different hypotheses. For example, here, you could have the standard model versus one of the anomalous hypotheses, and the interference, which tries to really collect all the information for the interference between different components. Also, our discriminants use and try to exploit all the available information, both from production and decay. In the next slide, you can see a characteristic event in the VMBF tagged category with very nice VMBF topology, where you can see tune jets in the really forward areas being associated with two opposite sign pairs of leptons, which possibly this could have come from a vector boson fusion event of the Higgs decaying to 4 leptons. Results. In the next sections of this presentation, I'm going to be showing results. And then what we start with is the bosonic couplings using the first approach in terms of the relations between the anomalous couplings. As a reminder here, as I said, we have 5 independent couplings, 4 anomalous ones, which you can see here with the scans FA2, FA3, F lambda 1, and F lambda 1 in gamma. We perform 2 types of scans where we either fix the other anomalous contributions to 0 or we profile them, and you can see the difference. And then we also do 2-dimensional scans. You can see that there are many minima that we observe that are away from 0, but everything still is consistent with the standard model. In the next slide, you can see the remaining of the 2-dimensional scans that we have done. And you can see the interesting interplay between the different anomalous couplings and their correlations. Following the results of the first approach, we have the results with the second approach, where the EFT relations actually have been implemented between the anomalous couplings. In this case, the number of independent couplings is reduced to 3. And you can see here the results. What is interesting here is that the stringent limits are set on these anomalous couplings, and everything is consistent with the standard model. In the next slide, I have an interpretation of these couplings in terms of the Lagrangian coefficients. And so what we do is that we do 1-dimensional scans of these Lagrangian coefficients, CZZ, for example, CZ box. CZ tilde is the one that corresponds to the CP violating anomalous coupling. And furthermore, we again perform 2-dimensional scans of these Lagrangian coefficients with the EFT relations implemented. And here you can see the remaining, again, plots from the 2-dimensional scans and the interesting patterns that exist. Then a measurement of the gluon-Higgs coupling is performed with the Higgs decaying to 4 leptons. Here, the idea, of course, is to use the production vertex to measure this coupling. And we measure the CP-sensitive FA3 in GGH. You can see the scan here. And then what we do is that we can, under certain assumptions, of course, interpret this measurement in terms of the Lagrangian couplings C in G tilde and C in G. What is very interesting here is that the mu measurement sets the radius of this ring that you observe, and the FA3 measurement resolves what happens inside this ring. And basically here you can see that the results point to a maximal mixing between CP odd and CP even, the CP odd and CP even components, but still, again, consistent with the standard model. Following the bosonic couplings, we have here a report of the Yukawa Higgs top coupling. We want to study the CP structure of this using this so-called FCP HTT. And this is done in two different decay channels. It's done in TTH with the Higgs going to 4 leptons, and also TTH Higgs to gamma and gamma. It's important to mention here that actually the measurement in Higgs to gamma and gamma also coincides with the first observation of TTH in a single fully reconstructed channel with a 6.6 significance. In the case of the Higgs to gamma and gamma and also to 4 leptons, here MBDT is utilized to measure to measure this FCP. And then 12 different categories are defined where the mass of the diphoton system is measured. Then what we do is that we interpret the results as top couplings.
2 minutes, 2 minutes left.
Thank you, thank you. So one can also then proceed and use the gluon fusion events and assume that the gluon fusion Higgs loop is dominated by standard model particles, and in this case, most probably TOBs, and then use that in order to perform a measurement of the KF and KF tilde. This is exactly what is done here. Results are combined between 4 leptons and Higgs to gamma and gamma, and you can see the results to the right. Another interesting result from CMS, even though one that was released a couple of years ago, is an off-shell analysis of the Higgs decaying to 4 leptons and measurement of the anomalous couplings. What is interesting here is that there was a measurement of the anomalous coupling with the standard model, with the width of the Higgs in tandem, as you can see with the 2-dimensional scans here. And yes, this was using a combination of run 1 and partial run 2 data. And also here, individual anomalous coupling scans have been performed. So concluding, I have presented to you today dedicated measurements performed by CMS for the Higgs anomalous couplings. These measurements are of paramount importance for the LHC experiments for many reasons. First of all, they are excellent probes for physics beyond the standard model up to really high energy scales. CMS investigates these anomalous couplings in many different multiple final states and then tries to combine them. And then also, as I have shown, effective field theory relations have been implemented, for example, in some cases, and interpretations in terms of the Lagrangian coefficients are also performed. Thank you for your attention.
Okay, thank you for the nice summary on these anomalous couplings. So questions, please. Yasu, yeah, go ahead.
Okay, can you hear me?
Yes.
Yeah, thanks a lot. So I have a general question for the anomalous coupling measurement in the CMS. So I guess that the regular analysis for the Higgs is optimized with respect to the standard model assumption. And in order to measure these anomal couplings, have you already re-optimized the analysis with respect to the, how to say, the kinematics for the different assumptions?
Yes, exactly. So actually the results presented today here are a dedicated analysis where there is a fully optimization based on the anomalous couplings, actually, not on standard model.
I see. And if we have the 5, for instance, 5 anomal couplings, so what is the strategy to optimize the analysis?
So the strategy is this categorization scheme that doesn't only rely on rejecting background versus standard model, but actually uses these matrix element-based discriminants so we actually use a vector, if you like, of discriminants where an event is considered to pass our categorization and be selected if it passes a string of these discriminants, each one of which is dedicated to a specific anomalous coupling.
Okay, thanks a lot. It's clear.
Okay, thanks. Any other question? So if not, then thanks again. And
sorry to interrupt. I just wanted to mention that I will also have a Zoom link for further discussion for anyone.
Okay, yeah, good point. Yeah,
Thank you. Thank you.
Written on the sites. Okay, perfect. And by the way, since you mentioned that, so I should remind people that they should also, the speakers, they should also watch MetaMost. There is already at least one question already for one of the speakers of today morning. So anyway, so thanks a lot, Savas. And now let's move to the Atlas combination by Matthew.
Okie dokie. Okay, can you see my slides? Can you hear me?
Yes, perfect. Go ahead.
Okay, great, thanks. Okay, my name is Matt Klein, as is clear from the slide, from the University of Michigan, and I'm going to discuss the combined Higgs boson measurements of the ATLAS experiment. So as can presumably be gathered from all of the other talks within this session, there are many different ATLAS Higgs measurements, both new and old, generally divided between measuring different Higgs decays. In practice, though, these different measurements are often measuring the same basic underlying quantities, such as GGF cross-sections, TTH cross-sections, and particle couplings. So that's where the ATLAS combination comes in. The way it works is we just combine existing ATLAS measurements in order to make the most precise measurements possible of Higgs boson properties with ATLAS, and also then to be potentially sensitive to various different types of BSM effects that are present in different models. The previous combination used 2015 to 17 data for some of the final states, but still 2015 to 16 for others, and some weren't even included that have been added now. Whereas the main change from this combination is at least the increase of the data set for some of the final states up to use the full run-2 data set of 139 inverse femtobarns. So the summary of all of the different analyses and production processes that are considered is shown on this slide. ZZ4L and gamma gamma tend to be the most precise in terms of the object precision that's actually involved. However, they also have low cross sections, which tend to limit their precision of the actual measurements. So increasing to the full run-2 data set in itself already results in a greatly increased precision of the measurements for this combination. Beyond this, though, there are substantial analysis improvements, especially in terms of improvements in categorization to decrease the correlations of the measurements of different properties, which also then results in an increased precision. For BB, VBF, and TTH are still using the 15 to 16 data sets, but VH has now been increased to use the full run-2 data set, which in particular results in increased precision for the measurement of the B quark coupling and also for VH cross-sections. Mu has been increased to the full run-2 data set. And also, given that this is statistically limited as a process, this is a greatly increased precision for this result. But also, different production processes have been added since the last result, in particular VH and TTH. Tau and WW are still using 2015 to 16 data for this result, but as can have been seen in an earlier talk, WW in the VBF production mode does have a new public result using the full run-2 data set that's just not been included in the combination yet. Multi-lepton is a focused analysis for TTH that's still using the 2015 to 16 data set, but Higgs to invisible, which is uniquely sensitive to constraining invisible decays of the Higgs boson, has been updated for the VBF production mode to use the full run-2 data set. Okay, for the rest of this talk, I'm just going to give a set of different fits and different measurements of different Higgs boson properties, generally distinguished by just setting certain quantities constant, making certain assumptions, and then measuring certain quantities under these assumptions. The first measurement is just measuring the global signal strength. So just defining a single parameter as a correction to the standard model cross-section for the Higgs, and then just floating that and finding the best fit value across all production modes and final states. The first thing to note is that the resulting value is 1.06 plus minus 0.07, which is well within the agreement with the standard model expectation. A second thing that's worth noting is that the statistical uncertainty at this point is subdominant with respect to systematic uncertainties. So improving this measurement in the future isn't going to be simply a matter of increasing the data set by taking more data. It's really going to have to require improvements in analysis and theoretical understanding of the Higgs. The next set of measurements is the measurement of the Higgs boson production cross-sections. So defining a parameter for each of the 5 major production modes, floating them and finding the best fit value for each of these different cross-sections. And for this case, only a reference is shown to the 2019 publication on the left, and then the new result is shown on the right. And the first thing to note is that improvements from the old to the new results aren't just in a single production mode. It's really across the board significant reductions in uncertainties, both statistical and systematic. Generally, the WH and ZH improvements are largely resulting from the improvements and extension of VHBB, GGF and VBF, and TTH generally from gamma gamma and ZZ. Second thing that's worth noting is that with the new results, we have greater than 5 sigma, so observation of all 5 major production modes with ATLAS, where we're defining the major production modes as the production modes that are defined on this slide, the GGF, VBF, WH, ZH, and TTH plus TH. So now that we've observed all the production methods, the next thing is to actually measure things in a differential way and more precisely. The next fit is just floating all of the different combinations of production mode and final state separately, both to check the consistency of the different results, to look for any sort of deviation that might pop up in ways that are unexpected, and to confirm just the standard model's agreement with expectation in general. The first thing to note is pretty much everything is pretty well within the agreement for the standard model. The standard model would be at 1, and everything, given the large uncertainties for some of the different processes, are pretty well in agreement with 1. The second thing is, incidentally, for a given production process, the different final states tend to be self-consistent. For GGF on the top, all of the different Higgs decays tend to give consistent measurements for the GGF cross-section. For VBF and VH and TTH, generally this is also true, though they also suffer from larger statistical uncertainties in particular. But in any case, good agreement with the standard model is observed for everything. Next is the simplified template cross-section. The way this works and the motivation for it has already been discussed multiple times in previous presentations, but just to give an overview. The way it works is we generally define a set of different bins, just dividing the production process cross-sections from the previous slides into different phase space bins, which are sensitive to deviations from the standard model expectation, that are generally not suffering from limited theoretical understanding. We don't want to define bins that have large theoretical uncertainty. And then bins are defined to be large enough such that we can actually distinguish them at analysis level. We don't want to define bins that are so small that analyses cannot actually distinguish between them such that they would suffer from large correlations and anti-correlations more specifically. For these measurements, we're only including gamma gamma, 4L, and BB final states, which also means this is a full run-to result. The results of the STXS fit are shown on this slide. As an example of the binning that's used, the GGF bins are shown on the left. Generally, there's 11 different bins, and different phase-space regions are potentially sensitive to different effects. For example, the high PTH bins are generally sensitive to certain types of BSM effects that might occur as new particles entering into the GGF loops, causing deviations in the high PT region. But generally, we find that everything is pretty well within the agreement with the standard model expectation. Because now we're dividing everything up into a large number of bins, the uncertainties tend to be more statistical here rather than systematic as they were on the previous measurement. But in any case, we don't see any large or significant deviations from the standard model. One other thing that's worth noting is that because of the regions that are defined in H gamma gamma in particular, we are able to set a limit on TH production specifically. And it's found to be a limit of 8.4 times the standard model expected cross-section. But also given that the expectation for this limit was 8.2 times the expected cross-section, this is also found to be very much within agreement for the standard model. Okay, everything up until this point has just been measurement of cross-sections and branching fractions of the Higgs boson. Of course, in practice, a lot of these different production modes and branching fractions are really the result of the same standard model particle couplings that actually would modify these particular cross-sections in the same way. For instance, the GGF cross-section and the Higgs to gamma-gamma decay are both largely the result of loop diagrams, such that a modification of, for example, the Higgs to top quark coupling would cause a deviation of these cross sections and branching fractions in the same basic ways. So the next thing is to actually look for deviations of the Higgs to particle couplings themselves. And the way this works is we define a set of modifiers, referred to as kappa in this framework, to the standard model particle couplings. There's a couple ways to potentially do this, either for loop diagrams in particular, which are potentially sensitive to different BSM effects. So for the loop diagrams of Higgs to gluon couplings and Higgs to photon couplings, we can either define kappa parameters as deviations of these effective couplings, or we can resolve all of the different diagrams and only define kappa parameters as deviations for the standard model direct couplings themselves. The former potentially would be sensitive to, for example, new particles entering into loops, which would not be the case for the latter, whereas the latter allows us to be more general in terms of looking for deviations of individual particle couplings. One other thing that's worth noting is the Higgs boson total width potentially would be affected by invisible or undetected branchings of the Higgs boson. So a couple extra parameters are defined that are potentially allowed to float in some of the results that I'll show, which are just the branching fraction for Higgs to invisible and the branching fraction for undetected decays, where in this case, invisible just refers to Higgs bosons that are invisible to the Atlas detector, which is to some extent constrained by the Higgs to invisible analysis, where the undetected branching is really anything that would not be detected by any other result, in particular Higgs to light jets, beyond the expected Higgs to gluons or CC bar from the standard model. Okay, the first of these results is just floating the resolved coupling for each of the standard model particles, setting the BSM couplings and branching fractions to 0, and then not using the effective couplings. And this is generally a classic plot. So the plot on the right then shows effectively the coupling to each standard model particle as a function of particle mass. And generally, we find very good agreement with the standard model expectation for all of the different particle couplings, which is really a testament to the success of the standard model and of the precision of Atlas measurements, that really we have such good agreement across 3 orders of magnitude in particle mass for the Higgs boson couplings. The next thing is floating the effective couplings to gluons and photons, keeping the other kappa parameters constant, and then potentially also floating the invisible and undetected branching fractions. And generally, this would potentially be sensitive to new physics entering into either loop diagrams, like new particles entering into loops, or in the invisible and undetected case, also new physics entering into Higgs boson decays. So the plot on the right shows the actual measured result. For these, the panel on the left shows what happens when the invisible and undetected branchings are set to 0. The kappa G and kappa gamma then are the best fit measurement for these parameters for the effective couplings to gluons and photons. And generally, everything is found to be very much within the agreement for the standard model. And it's the same on the right. On the right, the invisible and undetected branchings are allowed to float. The kappa G and kappa gamma are both found to be well within the agreement for the standard model, and upper limits are set on the invisible and undetected branching fractions of the Higgs. Next, this is what happens when, in addition to the previous model, all of the kappa parameters for the other standard model particles are allowed to float up to certain constraints that are placed in the model. And the results are shown on the right. First of all, setting the invisible and undetected branchings to 0 on the left panel, where everything is again found to be very much within the agreement for the standard model. And then in the panel on the right, the invisible and undetected branchings are allowed to float. And again, everything is found to be within the expectation, and upper limits are then placed on the invisible and undetected branchings. One other thing to note is that in this particular model, we're able to set constraints on negative kappa t, just because now there are regions that are actually defined to actually constrain it. And negative kappa t is constrained at the level of 2.9 sigma, expecting 2.7 sigma. So everything is also well within the agreement for the standard model.
Okay, 2 minutes left.
Thank you kindly. Okay, next is what happens when we float the actual ratios. So all of the models up until this point require certain assumptions to be made in order to actually be able to set any limits. And in particular, really all of the measurements previously have an explicit dependence on the Higgs boson total width. One thing that's worth noting is that if instead of measuring individual kappa parameters, you measure the ratio of kappa parameters, the Higgs total width cancels out, and this model is able to set more independent, or is able to set measurements that are more independent of assumptions than the previous ones. In practice, all of the different kappa ratios are found to be within the agreement for the standard model if you look on the plot on the left, which at least to some extent rules out various different types of BSM effects that one might expect. But in any case, if nothing else, this is a pretty strong confirmation of the standard model up until the precision that's actually measured in this analysis. Okay, there's many different types of models that predict other types of Higgs bosons and other types of BSM effects. In this particular combination, limits are set on the 2HDM. The way it works is just the observed Higgs boson is taken to be the light CP even scalar Higgs boson of the 2HDM, and there's just different interpretations for the different 2HDM types. The results are shown for the type 1 and type 2 2HDM on the bottom. In general, though, various regions of phase space are ruled out, but the allowed region of phase space is very much consistent with the observed Higgs boson being the light CP even Higgs boson of the 2HDM, up until the precision that's made in the analysis. Okay, so there have been a lot of results using combinations of existing measurements of Atlas with the Atlas detector, which have been discussed in previous talks of this session in previous days. Everything so far seems to be generally consistent with the standard model. If you want to know more about individual measurements, links are shown for generally talks within either the session today or sessions yesterday. If you want more information about Higgs boson combination, there's a talk by Max tomorrow on the combination for Higgs boson self-coupling constraints and measurements. And today there's already been a talk on the combination of results to measure Higgs boson cross-sections in a differential manner. And that is the end.
Okay, thanks a lot for a nice overview. So questions, please. Maria.
Hi, so thank you so much for the talk, and very nice to see the new combination. So I have just a curiosity. So in your previous slide, in the one of 2HDM, in the past you have also done updated combinations in some of the Bayesian standard model benchmarks. Have you done this time?
Which ones are we talking about?
HMSM or the
yeah, so that's not included in this particular combination. But yeah, it was in the previous one. But anything is possible in the future.
Okay, thank you.
Okay, any other question, please? So doesn't seem to be the case. So thanks a lot again. And let's move to the last talk of today's session by Ignazi. So can you share the slides?
One moment, yes, can you hear me?
Yes, perfect. Just share the slides and
yes. So then let me. Okay.
Okay.
Perfect. So then, first of all, thank you very much for the possibility of giving this talk here. Okay, as you can see here, the title of the talk is Constraining Resonances by Using the Electroweak Effective Theory. And this work has been done in collaboration with Tony Pic from Valencia and with Juanjo Sanciguero from Madrid. This work is related to the papers you can see here. Okay, I will go with the first one. Okay, here you have the outline. Okay, the outline of the talk. First, I will try to motivate the talk. So then I think that it's interesting, but I will try to motivate why we did what we did, and then we go to the framework, the effective Lagrangians. In this case, we have two energy regimes. At low energies, we have the electroweak effective theory, also known as Higgs effective field theory or electroweak chiral Lagrangian. This is what we have at low energies, where we only have the standard model degrees of freedoms. And at high energies, we have also these possible resonances. So then we have the resonance electroweak theory. We want to match both Lagrangians, trying to, as we have in the third point in the phenomenology, we want to estimate the bosonic low energy constants of the electroweak effective theory in terms of resonance parameters, trying to constrain these resonances we want to find. Okay, and finally we'll try to conclude. Okay, so then I could skip this slide really, but it's clear the standard model works pretty well. And here in this session we are thinking about the Higgs sector. Okay, so then it's clear that the LHC discovered a new particle around 125 GeV. But the point is that we want to be sure about the nature. This is what we are trying to do here. Up to now, everything is consistent with the standard model, okay? And we have not found a new particle. So then it's clear that we have a gap, okay? That we have a gap between the standard model and possible new physics particles, okay? So then effective field theories seems to be appropriate. And the point is that here, what we want to follow is, you know that sometimes in these effective approaches, we can follow a top-down or a bottom-up approach. In this case, we don't know what we have at higher energies. So then the idea is that we want to follow a bottom-up approach. That is by doing physics, as we are doing here with the LHC at these low energies, we want to get imprints of the new physics we have at high energies, okay? So this is the case. By doing physics at low energies, we want to get imprints or the new states, these resonances we could have at high energies. Perfect. So then, depending on the nature of the electroweak symmetry breaking, there are two possibilities, or something in between. The more common decoupling or linear effective field theory is the standard model effective field theory, where we assume a standard model Higgs, and the leading order Lagrangian is the standard model Lagrangian, really. And there is a typical expansion in canonical dimensions. But here we want to follow the more general non-decoupling or nonlinear effective field theory. There are different names in the literature: electroweak effective theory, Higgs effective field theory, or electroweak chiral Lagrangian. And this approach has been used in today's session by Carlos Quesada, okay? In this case, we assume a non-standard model Higgs, really is a scalar singlet. Okay, at leading order, what we have, as we have seen previously, we have the Higgsless standard model Lagrangian plus the pieces including the Higgs and the Goldstone bosons. There is an expansion in loops or chiral dimensions. There is a chiral expansion. And really some composite Higgs models can be described within the electroweak effective theory. It's important to stress that this general approach, a particular case of this general approach is the usual standard model effective field theory. Perfect. So then, as I have said before, we want to estimate the low energy constants of the electroweak effective theory in terms of resonance parameters. Okay, so then we want to determine this Wilson coefficient in terms of resonance parameters. But it's clear that if we don't do anything, we are going to have some couplings in terms of much more couplings. So then a very important ingredient of this work is the use of short distance constraints, really because of two reasons. First, from a practical point of view, we want to reduce the number of resonance parameters. If not, from a phenomenological point of view, we are not going to be able to do many things. And moreover, these resonance Lagrangians, we we understand them as a bridge between low energies and high energies. Okay, so then really for this interpolation, the short distance behavior, the use of short distance behavior is really an important ingredient. And then finally, we go to the phenomenology. Okay, so then we want to constrain the resonance masses. Okay, really, this game is very similar to what happens in QCD. In that case, in QCD, we have the chiral symmetry. Here we have the custodial symmetry. So then the chiral symmetry breaking we have there. In this case, we have the electroweak symmetry breaking. Really, by following a naive ray scaling, we would expect resonances at the TED scale. And this is what really we are going to find. Okay, perfect. So then in QCD, we have QCD. We know perfectly what we have at high energies. We know perfectly what we have at very low energies, chiral perturbation theory. And in the middle, we have the resonance chiral theory. And here we have at high energies, really, we don't know what we have. This is what we want to find here. Fundamental electroweak theory. Really, this is new physics, okay, beyond standard model. And at low energies, we have this effective approach, the electroweak effective theory. And in the middle, we consider this resonance electroweak theory. Okay, so then we have two effective Lagrange. At low energies, the electroweak effective theory without the resonances, so then with only the standard model degrees of freedoms, and at higher energies, we include some resonances. The main aim of this work, we want to estimate the low energy constants in terms of resonance parameters in order to go to the data provided by the experiments by constraint these possible heavy masses. So then the steps, first we need to build both effective theories. After that, we want to match them, and then we go to the phenomenology, the most interesting result of this work. We have said that the high energy constraints are fundamental, okay, because we understand this resonance Lagrangian as an interpolation between low and high energies. So then we can use information coming from high energies, okay, and moreover, we want to reduce the number of resonance parameters. We are considering here the Weinberg sum rules and vector and axial form factors to Goldstone are to Goldstones and Higgs, okay? Moreover, operators with a large number of derivatives tend to violate the asymptotic behavior. We know that this program works pretty well in QCD, okay? It's a very typical way of estimating the low energy constants of the next to leading order and the next to leading order of the chiral perturbation theory Lagrangian by using the resonance chiral theory and always by using the short distance constraints too. Perfect. So then this bottom-up approach. How do we build the Lagrangian? Here we have the typical ingredients of an effective Lagrangian. We need a symmetry, we need degrees of freedom, and we need a power counting. Here we have the custodial symmetry, the degrees of freedom, at low energies, the standard model particles, and at high energies, the previous ones, plus resonances, and we follow the chiral power counting. Summarized here. So then the way of working very similar to many effective approaches. At leading order, what we have 3-level contributions from the leading order Lagrangian, but at next to leading order, we have two kinds of contributions. We have one loop contributions from the leading order Lagrangian plus 3-level contributions from the next to leading order Lagrangian. So then we see from here that we have this typical order by order renormalization, okay? So then these next to leading order couplings are going to be renormalized. So then they run, okay? Perfect. So then we go the electroweak effective theory. So then without resonances, at leading order, we have basically as I have said before, the Higgs-less standard model Lagrangian plus the pieces including the gauge bosons and the Higgs. At next to leading order, we have now much more operators. And here I show really what is important for this work, because here we are interested in the bosonic sector. So then in the bosonic low energy constant. In any case, we have split the Lagrangian, taking into account the presence of not of fermions. Here we have one fermion bilinear, here two fermion bilinears, and moreover, I split with or without tilde, depending on the P even or P odd nature. The most important for us, as I have said, is these first 12 operators, P even operators, and moreover without fermions. At high energies, we have the resonances. So then we have the previous operators plus the operators including the resonances, bosonic resonances, vector axial scalar and pseudo-scalar resonances. We consider electroweak SU2 singlets and triplets, and QCD SO3 singlets and octets, and fermionic double resonances, but they are not relevant for the bosonic operator. So then we integrate out these resonances similar to the chiral perturbation theory case. So then finally we estimate the electroweak effective theory Wilson coefficient in terms of resonance parameters, and then we go to the phenomenology. Okay, so then after this integration, for instance, here I show for the operators we are interested here, we are able to estimate them in terms of resonance parameters. And the next step, as I have said, we use the short distance constraints, and finally we are able to estimate these low energy constants in terms of only a few resonance parameters. So then experimental, we go to the experiment. And then above all, we are interested about the low energy constant of the first operator, the third one, and the fourth and the fifth one. F1 can be determined by using the oblique parameters, so above all S, the S parameter. F3 by using anomalous triple gates couplings, and F4 and F5 by using anomalous quartic gates parameters. So then, moreover, we need this kappa W. We have been talking in this session about this kappa W is close to 1. We know that in the standard model, the value is 1, and the same for C2B is close to 1. The first one, kappa W, is the Higgs WW coupling in the end, and C2B is the Higgs WW coupling. Okay, so then this first one, kappa W and C2B, we need them for the running. Okay, but then we see that really the information F1, F3, F4, F4 plus F5, close to 5. We don't have very good numbers, but they are enough. The point is that they start to be competitive in order to get imprints of the resonances. From one loop consideration, we would expect 10 to minus 3, the order of magnitude, and the running the same, 10 to minus 3. And I go to the main result. Okay, here I saw these parameters, and here I saw the ones where we have experimental data. The experimental data is the green band, and the dashed green band you have here, okay, is the one when we consider moreover the running, because we know the running, because the running is established, and this is the running that depends on some parameters, on this kappa W and C2B. The most important one is the one coming from F1. And then here I show the dependence of this F1 in terms of the vector mass, okay? In gray, if we consider the first and the second biversal rule, and if we consider only the first biversal rule, we have both the gray and the orange band, okay? And here in orange, blue, red, and gray, we don't know the axial mass. So then we assume that the axial mass is infinity. We have the gray line. If we consider 1.2 times the vector mass, the red, 1.1, the blue, and if we assume that the axial mass is equal to the vector mass, the orange. So then we assume we expect to be close to the blue or red one. From here, what is clear is that we need to get resonances at the TeV scale larger than or equal to 2 TeV, more or less. Here with F3, by considering only P even operators or P even plus P odd operators, only the black or the gray band. The same with F4. Okay, in this case, we need to consider the first and the second biversal rule, and we assume only P even operators. Okay, and I have followed the previous notation, the orange, the blue, the red, and the gray band. And finally, F4 plus F5. In this case, it depends on another coupling, but is, as you find here, is a good place to search for scalar resonances. But the point is that from this, all with the first one, from here, we see that really we have competitive data in order to start to constrain these possible resonances, okay? All the couplings are consistent, okay, with the, or can be consistent with the standard model, but in any case, with these numbers, we can say something about the resonances we wanted to say, we wanted to constrain. Around this, all the first one, F1, with the one which comes from the, in the end, from the S parameter, oblique parameters larger than or equal to 2 TeV. Okay, here I saw F6, F6 plus F7, and F9. In this case, we don't have experimental information in the future, but we have the theoretical predictions prepared, okay? So then here I go to the conclusions. Up to now, all searches for new physics have given negative results. So then for sure, we have a gap between the standard model and possible new states. So then effective field theories are appropriate. And we have two possibilities for these effective field theory approaches depending on the breaking standard model effective field theory. Really, the most common standard model effective field theory, and here we prefer to use the more general electroweak effective theory, where we follow expansion in loops or chiral dimensions. Everything similar to the QCD case. So then we wanted to estimate the Wilson coefficient of this electroweak effective theory Lagrangian in terms of resonance parameters by using short distance constraints in order to be able to fix everything in terms of a few resonance parameters. And then by looking at the previous slides, what we have found is that really the experimental LHC constraints start to be competitive, and there is room for these resonances, and they are at the TeV scale larger or equal to 2 TeVs.
Okay, thanks a lot, Ignacy. So questions, please. So I don't see any hand raised. So maybe I have very naive question. So given the experimental progress we have seen yesterday and today, which one of these scenarios will be more constrained after these updates?
Okay, so then the point is that exactly, data really we have used very recent years from very recent data from this year or last year, and moreover they are improving. Okay, so then avoid we have information with this F1, F3, F4, and the point is that the scenario seems to be possible. Okay, and all these vector resonances could be found in the near future. This is the point. So then that we are optimistic. Okay, that the data are improving very fast. And then the point is that we are going to be able to know if they are there or not before we thought a priori. This is the answer.
Okay, thanks.
Okay, welcome.
So any other question, please? So if not, then let's thank Ignacy again. And just let me remind you that there is still a MetaMouse channel open for any questions to any speaker. And also there were 2 speakers of this morning who have opened a specific Zoom room for questions, for discussion specific to the JHU generator and the anomalous coupling measurements. So thanks all to all the speakers and participants of today, and there will be a poster session in about half an hour starting from now in the same Zoom room. So see you there, or eventually tomorrow. Tomorrow at the third Higgs session. Okay, thank you.